Tejinder Singh Sagu. He is professor in Peck University and Technology, Chandigarh, and he is here to give you a lecture on power quality issues and its improvement. And he has done a lot of research in this area of power quality, and he has number of papers to his credit in both international journals and conferences. And I just hand over the session to Dr. Tejinder Singh Sagu.
Good morning to all present. The topic of our presentation is power quality issues and its improvement. So the main contents to be discussed in this PPT are, first of all, the definition of power quality. What is power quality? Then various types of power quality problems due to which the degradation in power quality is there. Then how we monitor the power quality. Then fourth is the is a brief introduction regarding the power quality deregulation, and finally the different level of actions which we need in power quality improvement. So these are some of the questions before starting our talk. That what is the cost of power quality? What is the value of power quality in future? How are the customers addressing power quality needs and risks? And what needs to be done, means what are the various solutions to these type of problems. So this is a very simple definition by which we will define the power quality. So power quality is a serious issue that touches almost all the industrial, commercial and residential customers in some way. So any customer, whether he is a industrial customer or he is a commercial customer or he is a residential customer, everyone is nowadays facing the problem of power quality in some of the other ways, which we are going to discuss. This is the exact definition of power quality, that any power problem manifested in voltage, current or frequency deviations that results in the failure or disoperation of the customer equipment. Fine. So we are having a proper voltage. For example, for single phase it is 230 volt. Current is also specified for every device and frequency is 50 hertz. So if there is any deviation in any of these quantities, then there will be deviation in the power quality and the equipment which is being connected will be disoperate. So of all the power quality problems, approximately these are the percentage wise breakup of various power quality problems. 60% are the internally generated within the home or business or industry. Means 60% of the problems are originated from the source itself. The 20% are the result of the neighboring customer. Neighboring customer simply means that if a common line is supplying two customers, so if one customer is having very heavy load connected to his credit and other customer is only having a simple load, then one customer is affecting the other because they are being connected to the same network and same transformer is supplying the power to both the customers. The third is 15% are the result of the natural phenomena such as lighting, tree limbs and animal contacts, which are very rare. And 5% are the normal utility operations such as the operation of a circuit breaker, relay or any other switchgear and protection device which is being operated. This is another definition of power quality from other point of view, that the concept of powering and grounding the sensitive equipment in a manner that is suitable to the operation of that equipment. Nowadays power quality problem is due to most of the sensitive equipments we are using nowadays. So sensitive equipment we define in a way that if there is any small deviation, for example we are having 230 volts, so if there is a variation of plus minus 5 volt, let's say, then this sensitive equipment will detect it and it will not behave in a proper manner. So we have to take with the caution that within the industry the alternate definitions or interpretation of power quality have been used. There are plenty of power quality definitions, so reflecting different points of view. So therefore this definition might not be exclusive pending development of a broader consensus. So power, or you can say voltage disturbance, or you can say power quality, It is nothing but a point of view of an equipment designer or manufacturer. Might be that the power quality is a perfect sinusoidal wave with no variation in the voltage and no noise present on the grounding system. Whenever we buy any equipment from the manufacturer, then he will always be saying that my equipment is giving us the perfect sinusoidal wave and there is no deviation in any quantity in this. So another point of view, if we take from the engineer's point of view, it is that point of view of an electrical utility engineer might be that the power quality is simply voltage availability or outage in minutes. Means the engineer will only look after the voltage availability, that power is there or not, and when power is not there, then his role is only that the power is not there, and now his role is going to be there. And finally, a point of view of an end user, means customer, is that power quality or quality power is simply the power that works for whatever equipment the end user is applying. For example, if we are having plenty of equipment which are being connected, so customer is always expecting that my equipment will behave in a proper way. So power disturbance is nothing but any deviation from the normal value, as we had already discussed. So when monitoring electric power with many devices, the thresholds are established to define what constitute a power disturbance. We generally establish a threshold value, and often these values are determined by the type of problem that is occurring. Means there are plenty of power quality problem in the coming slides which we are going to discuss about these power quality problems. So these are the challenges, some of the main challenges of the power quality, that there should be flexibility in the operation, there should be reliability, it must be comprehensive, and most important, it must be cost effective. So the technical facts regarding the power quality are that the main are steady state issues, transient protection issues, electrical noise issues, and wiring guidelines issues. We are having certain types of, for example, we are having, if we are considering a complete power system diagram, then we are having generation, transmission, and distribution, and then every level we are having different type of equipments which are being connected. So these are the various issues which are concerned with every level. So now the exact definitions are coming up, that power quality is a business problem. Business problem means that loss of productivity, idle people, like we are seeing in a figure, and equipment, lost orders, goodwill, customers, and profits, lost the valuable transactions and orders not being processed, of course, the revenue and accounting problems, customers and management dissatisfaction, and overtime required to make up for the lost work time. If there is no power, then we cannot do anything. We are helpless. So according to a survey, Electric Light and Power magazine, that 30 to 40% of all business downtown is related to power quality problems. Means 30 to 40% of the all business problem is only related to power quality, especially. So this is the picture describing that power quality is such a big problem, as we are seeing in the figure. It is self-explanatory. The sensitivity of today's electronic equipment makes it susceptible to power disturbances which are there. So for some devices, a momentary disturbance can cause scrambled data, interrupted communication. For example, if now we are connected through a communication network, if there is small variation, then all the communication will be lost, and you know what will happen. A frozen mouse, system crashes, and equipment failure. This may be the worst case. So these are some of the headlines regarding the power quality problems from the various magazines and newspapers. Like if we are saying that second headline, that $50 billion per year in the USA is lost as a result of power quality breakdown. This is main headline. And fourth one is a voltage sag in a paper mill can waste a whole day of production, and you can see the loss regarding this, and so on. These are the various headlines. So now the question is that who is being affected. Like we had discussed, that all the customers are affected, whether he may be industrial, he may be commercial, or he may be residential. So we have now described them into various groups. First of all, the high cost facilities, for example, semiconductor plants, pharmaceuticals, data centers, these are the high cost facilities. And then medium cost facilities are automotive manufacturing, glass plants, plastics, chemicals, textiles, and so on. So what will happen? Of course, loss of production, scrap, cost to restart, labor cost, equipment damage and repair, and other costs. Means all of these problems are directly or indirectly are being linked with the power quality. So these are some of the basic principles, but they are very integrating, that we are having lot of expectations from the power quality. For this we need various specifications and minimum requirements. So why are we concerned about power qualities? Because the consequences of power quality problems, which we are going to discuss, the cost, various costs associated with this, and the benefits of the power quality design. Means if we are proposing any circuit to improve the power quality, then how we are designing that circuit. So what are the sensitive loads, what are the various sensitive loads which we are talking, and what is the life cycle to power quality issues, costs and benefit. So these are the various integrating principles. For example, understand the basic problem, that why the power quality is happening. Find the real cause before you find the best solution. We have to see the real cause, that there is a voltage sag, or there is a voltage swell, or there is a voltage variation. Then we have to propose a solution. First we have to see that what is the real cause of this problem. Then of course the third point is the solution must be always cost effective, because a customer always want that whatever the solution we are proposing for power quality improvement, so it must be cost effective, otherwise he will not be interested in this. So be open and work closely with the customer. This is very important. We have to be open and work very closely according to the various needs of the customer. Be proactive, of course, not reactive in this. And do not go after magic solutions. There are plenty of devices. You can see the various advertisements in the televisions or newspaper that this is the circuit we have proposed, and this will do the magic, and your electricity bill will be saved around 90%. So these all are magic solutions, so we must avoid these type of solutions. So most important point is that educate the utility and the customers. The utility and customers should be aware that what is there in the power quality and how it is going to improve. So we should not go for a magic like solution for this. Offer alternate power quality services. Of course we have to provide the services to the customer, and be aware of the legal issues. Of course, whenever we are buying any new equipment, then there is always various legal issues which are being concerned with that equipment. So we have to read very carefully all the documents if we are buying any sensitive equipment, and satisfy the customer. This is the main point. They are always right. If the customer is not having any problem, then he will not call you. If he has problem, then he will definitely call you. So these are some of the measurements. These are the various standards which are being proposed at international levels. We are having IEEE standards. We are having IEC standards. IEC means International Electrotechnical Commission, and we are having European standards. For example, for measuring the voltage flicker, and then we are having IEC 61000 standard. Then for harmonic it is different. Then for class A, class, these are the various classes of equipment. And for energy measurement, this measurement is different. So if we are talking about the American standards, then the American basically follows the IEEE standards, and IEEE 519 standards are basically defining all types of power quality issues and their problems. Now this is the integrated picture regarding the power quality. You can see that we are having this system monitoring. Fine. Then we are having system studies. Then what we are doing, we are calculating the actual performance from the two, that we are monitoring the system and then we are studying it. Then whatever the actual performance we are getting from these two, then we will compare this with the indices or reference value which is given. Because on this side we are having the expected performance, what we are desiring from that. So in this comparator block we are measuring the actual performance with the expected problem, and of course the output of that comparator is that we have to identify the various responsibilities and various solutions that we are getting from this comparator, and then we have to implement these solutions and we have to assess the performance of various types of solutions, and finally we have to make a report of this, and this report should be periodic. And then the feedback from this report is being as it is a closed loop system, then it is being fed to the again industry through the education and information programs, and then you can see that it is a closed loop system. Feedback is very important, means whatever the solution we are proposing to a power quality problem, whether it is meeting our requirements or not, and what are the various problems in this. So this is the feedback we obviously require from the reports itself, what we are generating from this. This is the single line diagram. You can see that we are having three types of system in this. One is utility services, then facility system, and then any industry. For example, in this particular diagram we are taking the example of a wafer processing system. So at the utility level we have to monitor the power quality and we have to see the various conditioning issues of this. Then at the facility level we have to see the various electrical distribution systems which are being supplied from this utility, and various infrastructure equipment which are being connected to it, and of course there is a support equipment, means if there is any problem then there is a support equipment which is being attached to this. And ultimately this is the wafer processing system, and it may be any industry, not particularly wafer processing system. So means there is any process which is there. So you can see that the input of all the utility facility system and ultimately the wafer processing system, they are being dependent upon each other. Now we will see the various types of power quality problems what we are going to discuss. For example, in the diagram you are saying that this is a problem of a voltage sag. For example, you are having a proper magnitude of voltage, but suddenly the magnitude of the voltage will drop down. Then this type of problem is known as voltage sag problem. And the typical duration of voltage sag is you can see that 0.5 to 30 cycles for the instantaneous. For momentary sag it varies from 30 cycles to 3 seconds, and for temporary sag it varies from 3 seconds to 1 minute. And if there is 1 minute voltage sag problem, then we will lose all the processes which are being connected to it. Now second example is voltage swell. Voltage swell means we are having a normal magnitude, then suddenly the magnitude of the voltage rises. Then again we are having three categories of this. One is instantaneous, second is momentary, and third is temporary, and accordingly their typical duration is shown. Then third category is interruption, voltage interruption, what we commonly term it as, means there is no power for some definite period. So it may be momentary interruption or it may be temporary interruption. And if it is temporary, then it can vary up to 10 seconds. The fourth category is long duration interruption. The previous category we have discussed, it was momentary interruption, but in this it is long time duration. So means we are having sustained interruption or under voltage or over voltage, but that duration is greater than 1 minute. So if this type of problem is there, then we term it as a long duration variation in the power quality. The fifth is the voltage imbalance or waveform distortion. You can see that at some point there is a distortion in the waveform, and hence there is a voltage imbalance. Next is the harmonics, which is the main problem of power quality. We are having DC offset value, harmonics, or interharmonics, means harmonics originating from harmonic itself. So due to this harmonic, there is a lot of variation, and there is a term total harmonic distortion, which we are going to discuss in the coming slide, which will define this harmonic. Harmonics are the major source of power quality problems nowadays. For electrical utilities, control of voltage and prevention of outages is power quality. Now for IEEE standards, you can see they have defined now in a table way, they have defined various types of problem. The thing is same what we had seen, but in a tabular form, nothing else. Now we will see the harmonic content. For example, in first figure you are seeing that it is a perfectly sinusoidal waveform, but in second case there is a fifth harmonic issues in this. So the resultant waveform will be like this. So you can see there is a lot of distortion in the waveform, and originally it was there and now it is there. So you can see the disruption in the power quality due to this fifth harmonic. So now this fundamental value function will become sin x, which is the original value, plus the fundamental value of harmonics, which we are getting from this fifth harmonic. So here we are having some standards for standards and definition for harmonic measurement. For example, the first two definitions are for total harmonic distortion, THD, and its value is different for both voltage as well as current. The formula is same, but in case of first it is only referring to voltage, and for second it is only referring to current. So it is nothing but the values we are taking, and we are taking the first value, base value, we are dividing it by, and then it is always being expressed in percentage. And third is the TDD. TDD means total demand distortion, and TDD is generally in terms of current, because whenever any equipment we run, then it is carrying the current from the voltage. So total demand distortion is always expressed in terms of current. And what is the difference in this? That in first case we are dividing by the fundamental value I1, and now it is being divided by the maximum demand what we are getting from the system. So this is the only difference between THD and TDD. So it is the important term K factor. So K factor is a very important term. Whenever we are discussing the harmonics, K factor is nothing but it is the transformer derating factor. So K factor is the weighting of the harmonic load currents according to their effects on transformer heating. So simply, if we are speaking, a K factor of 1 indicates a linear load, means if we are having a value of K factor of 1, then we are having no harmonics in the system. And higher the K factor, so greater will be the harmonic heating effect. Means if we are having greater harmonics in the system, then the life of the transformer will get reduced. So this K factor term is denoted this term only. Now you are seeing the power factor and cos phi, obviously it is the power factor. So they are also being dependent upon the total harmonic distortion. Means if there is a high distortion, high harmonic level in the waveform, then our power factor will always be affected by this. Now you are seeing the utility sources, and you are seeing the internal sources. Like in the Second slide we had discussed this 60% of the problems are originating from the internal system itself. Then these are the various utility sources, as you are seeing: lighting, power factor correction equipments, various types of faults, switching equipment. And on the other hand, the internal sources are the individual loads, for example any lighting, any ACs, elevators, HVAC equipment, any UPS which is being connected, VFDs, variable frequency drives, the battery chargers, the large induction motors during startups, electronic dimming systems, lighting blast, especially electronic blast. Nowadays we all are using CFL lamps, but their main limitation is that whenever we are using CFL, then there are more number of harmonics than compared to a ordinary bulb. Then main sources of distortion of power quality are arc welders and induction furnace or arc furnace. These are the main sources of power quality degradation. Then we are also using the medical equipments which are very sensitive. For example, MRIs and X-ray machines. They are also the sources of power quality degradation. Other equipments, computers, and various wiring issues. So these are all the internal sources which are the main sources of power quality degradation nowadays. So a comprehensive research in Europe in 1400 sites were conducted at the 8 countries reports that 20% experience the following: that computer lockouts are 20%, light flickering 22%, electronic card failure 18%, power factor correction system 17%, failures in high load switching 16%, and so on. So this is the percentage wise breakup through a research which was being conducted in the 8 countries of Europe. Now these are the various power quality problems, their major sources, and their solutions are being proposed. For example, first is the power quality problem of frequency. Then major source of this is utility. There is frequency variation, then of course it will be from the utility side. It is not like that the customer is doing something and the frequency variation is there. Voltage variation is by changing the load. If we are having number of loads which are rapidly changing, then it will lead to the voltage variation. Then third is the voltage, then voltage dip or voltage sag, then interruptions, then over voltage, then transients, unbalanced, harmonics. For example, if we are having harmonics, then the major sources of harmonics are various nonlinear loads. So solution to this is that we can propose various types of filters, whether it may be active filter or it may be passive filter or it may be hybrid filter, or we can use any type of custom power device for the improvement of power quality by improving the harmonic level. This is the pie chart which is showing the various type of power quality problems. For example, if you are saying that the 56% of the power quality problems are due to voltage sag, 56% problems. Then voltage swell is 31%, voltage spike is 7%, and voltage outage is only 6%. So you can see that voltage sag is the main source of power quality problems in the industries. Now you can see that how the cost is affected due to voltage sag. Now you can see the various types of industries like textile, plastics, glass industries, process industries, and semiconductors. And if you are seeing where semiconductor industry is involving, then you can imagine the cost. You can see the cost level. And then for different industries, the cost level is varying. It is different for different industries. Then you can also see the cost of the momentary outages. Momentary means, as we had seen, that if there is variation for some seconds only, then there is so much loss due to these industries. For example, semiconductor, electronics, pharmaceutical, glass, and so on. So you can see the minimum and maximum kilowatt hour demand of this, and in terms of cost it has been expressed. And for commercial sector, if we are talking about, then mainly hospitals, banks, civil services are there. Then restaurants, commercial shops. These are the small sources. Otherwise, the main commercial sources are hospitals, where we use sensitive equipments like MRI machines and X-rays, etc. Now our next topic is power quality monitoring. That how we are monitoring the power quality. So power quality monitoring provides a continuous health check of a facility's power system. For example, harmonic interaction between the loads and power conditioning equipment spotted, high inrush current from equipment startup detected, transients from the load switching are seen. It provides data to see, diagnose and avert the looming problems, like trends can be detected, whether it may be the trend may be due to the voltage sag or voltage swell, and just in time equipment maintenance programs can be established. And it acts like a black box on an airplane to tell you what, when and where a power quality event occur, because power quality is mainly dealing that what is the main problem, when did it occur, and where did it occur. So the main function of power quality monitoring is this. And continuous power quality monitoring detects, records and leads to the prevention of power quality problems. So what is needed for this monitoring of power quality? So power quality monitors must detect and record the 7 types of power quality problems. Main is transients, then voltage interruptions, then voltage sag, or you can say under voltage, then voltage swell, you can say over voltage, then waveform distortion due to harmonics, then voltage fluctuations, then frequency variation, if there is frequency variation from the utility side. And these include flicker and complies to various standards, IEEE standards, ISO standards, and so on. So plus they must be, of course, they must be easy to use. If we are using any power quality monitoring equipment, then these are some of the characteristics of that monitoring equipment, that it must be easy to use. It must be suitable for continuously monitoring indoors and outdoors problems, and interfacing with the standard power quality analysis software. Nowadays plenty of softwares are available. We will also discuss one of the software at the end. And it must be fast enough to capture high speed events that produce equipment problems. The speed of that equipment must be very fast, and it must have enough storage to save the waveform you need. Because what is there, if a power quality problem had occurred, then we have to store this data, and we have now to study this data, that what is the main problem of that power quality problem, and in future it may not occur, so we have to study this data. So we can only study if it is being saved anywhere. So it must have power quality analysis tools which produce usable, actionable and valuable recommendations. So these are various steps which are being involved in the power quality monitoring, that what sensitive electronic equipment is experiencing problem. For example, what type of equipment and what is the location. Then nature of the problem, that what is the nature of this power quality problems, means whether it is causing data loss, it is causing the lockups, or it is causing the component damage, etc. Then when do the problem occur? For example, time of the day, day of week, particular system operation. There must be any problem that it is only occurring during the daytime or during the night time. So we have to see that when do the problem occur, and how long have the problems occurred. For example, since the installation of the equipment it is occurring, or just recently, or seasonally. So we have to see these type of problems. And coincident problems occurring at the same time, means light flicker, motor slow down. It may be happen that there are 2 or more problems which are occurring at the same time. So what are the possible problem sources at the site? For example, what are the main sources which are causing the degradation of power quality? For example, arc welder, air conditioning, UPS, and any non-linear source which is being connected. what is the existing protection for equipment, what is the solution which we are having at the site, and has the protection equipment helped the problem, the equipment we are having, had it helped the customer or not, and has the wiring and grounding of the building been checked, because most of the time the grounding issues are mainly the reason for the power quality problems. And has the quality of the supplied AC voltage been checked? For example, it may be checked through a 2 RMS meter or through power quality analyzer. So we have to check the quality of the supply voltage from which it is coming. So it is at the different, there are different levels regarding the power quality monitoring. For example, from philosophical points of view, which we had discussed, then from management point of view, and then from technical point of views. These are the at various levels we can monitor the power quality. Now this slide shows the overall percentage of the various reasons for power quality problems within the facility itself. For example, if we are having EMO circuit, for example, any switchgear or protection equipment, then 47% is the overall percentage that it is causing the power quality. Then DC power supply is 19%, three-phase power supply is 12%, vacuum pumps 12%, turbo pumps 7%, and AC inverter drives 2%. Now the question is, why are we concerned with power quality? As we had discussed, the power quality is directly related to the cost. If there is degradation in the power quality, then it is giving us the loss. So this loss is being expressed in terms of dollars in the, as you can see the diagram. So cost categories are the loss of production, scrap, restart cost, labor cost, repair and replacement cost, process inefficiency. These all costs are being dependent upon the power quality. And if we summarize it, then power quality is an integrated sum of A, B, and C, where A is electrical parameters, B is economic parameters, and C is the structure of the sector. The A, B, C are, now we are defining what is A, what is B, and what is C. For example, the A mainly we are accessing the power quality cost for the utility. For example, there are three main issues in this: that kilowatt hours not distributed, investment, what is the main investment is there in the power quality, then what are the various legal issues, then these three are the main issues which is giving us the parameter A. Then this is parameter B. Parameter B means accessing the cost of mitigation for the utility, various type of disturbances, level of quality, and what are the which is the cost, what is the cost of that mitigation of that power quality problem. And finally, this is the C. C means what are the main market effects on this, what is the return on investment if there is new customer, reduced losses and improved efficiency. Then this C is mainly accessing the power quality benefit to the utility. So main is A, B, and C. Now they are being combined. Now you can see that cost of disturbance A, cost of mitigation B, and benefit due to mitigation, this is C. So this A plus B plus C, this is now giving us the net benefit, and hence we can calculate the payback period from the solution proposed due to these problems. Now we will see some of the introduction regarding the power quality deregulation and why it is important. So power quality will have to be regulated. For example, as the deregulation takes over the industry, the temptation to let the level of service and investment in the system deteriorate is obvious. So various power quality indices are being developed and standardized to facilitate the characterization of power quality levels. So Electric Power Research Institute has completed a 2-year monitoring project to provide the benchmark indices describing the various power quality levels in the US, and in the same way the Europeans have done. And then utilities will have to report power quality performance statistics and make sure that the performance does not significantly deteriorate over the time. So what will be the power quality program look like? What is there in the power quality degradation? So power quality programs of the future will have a number of very important functions. They will coordinate system monitoring and analysis to benchmark the system performance. They can evaluate the various conditions of the and various priority wise. They can see the various conditions, and they will coordinate with the system planning and design groups to include the evaluation of power quality impacts in the system design. They will provide a full range of services for customers both within and outside their traditional service territories. They will install and maintain the equipment to improve the performance and energy efficiency. They will analyze the specific problems and develop various solutions, and then they will follow through the actual implementation management. They will develop the alliances with the equipment manufacturers and other service providers in order to offer system solutions to the customers, and they can take the advantage of quantity discounts. They will develop the expertise in these products and services so that there is an added value to the customer. The deregulation will not mean the end of power quality evaluation as an important function within the electrical utility industry. And on the contrary, power quality is only increasing in importance as competition, because the standard and utilities look for new ways to service their customer base. And how does the deregulated environment affecting the power quality? You can see that first point is very important: the reduced investment during the operation and maintenance. Then responsibility at various level, at economic level, at customer level, at utility level. Then power electronics penetration, transmission, distribution, and user end. Then distributed generation, various trends, various interconnected issues. Then regulating control, and then randomly varying sources. For example, if we are having a solar system being installed, or if we are having a wind system installed, then there are also power quality problems. Then we are seeing, because they are changing with the conditions of the day and night. So we have to see the randomly varying the sources. So what is new in power quality? We are having plenty of T&D technologies, transmission and distribution, instrumentation, modeling, etc. So now you can see the different levels of actions at various stages. For example, at the planning stage, planning is very important, because at the planning we have to see the power quality environment, and we have to do the surveys, and we have to do the various calculations that what are the various reasons, as we had discussed, which are causing the power quality degradation. Then second is the equipment specifications and development, and then third is the facility design and power conditioning specifications. So these all parameters are coming under planning and designing stage. Second is the solving power quality problems. Solving power quality problem means the power quality site surveys which are being conducted, whether it may be on site or off site. So equipment performance testing through various equipments, for example power quality analyzer or any monitor. Then design of various solutions, like we had discussed that for the harmonic improvement we are proposing active filter, passive filter, hybrid filter. Then we have to see the designs of various solutions. Then of course implementation and maintenance of these solutions, that how we are implementing these solutions to the utility. Ongoing operation services are mainly, they are power quality information services. There must be a customer help desk which is dealing with all the power quality problems. Then equipment maintenance and operation services, and then guaranteed power quality performance contracts. So now you can see that at the various levels, for example at the transmission level, then at distribution levels, then at end user, we are having different issues for the power quality. For example, if we are talking about the transmission, then the main problems are the voltage flicker, then the harmonics at the point of common coupling, both voltage harmonic and current harmonic. then voltage sag or interruption, and then capacitor bank addition. So these all are the issues which are being dealing with the transmission. And then second is the distribution concerns, and mainly in distribution harmonic is the main source of distribution. Then voltage sag phenomena, then voltage interruption, then various types of capacitor switching, then transient phenomena, and then finally the voltage regulation or voltage unbalance. So these all are the issues which are coming under the distribution. And finally in the end user, means on the customer side, we are having, as I had said, the grounding should be checked, that grounding should be proper. Then harmonics in the facilities, voltage sag sensitivity, transient susceptibility, voltage regulation, power factor correction, voltage flicker, the large motor starting measurement, and these all are the issues which are being taken into mind at the end user. So this is the evaluation procedure of the power quality monitoring. That first we have to identify the problem category. On the right hand side you are saying that whether it is voltage sag, swell, flicker, we had already discussed. Then after identifying, then problem characterization, that what is the main cause of this problem, what is the main characteristics, and what are the impacts on the equipment. Then identify range of solutions, then evaluate these solutions, and then finally optimum, we have to optimize these solutions. So finally, if you can measure it, if you cannot measure it, you cannot manage it, and if you can measure it, you can manage it. So this is the main important point from this presentation point of view. And now we will see the demo session of one of the power quality analyzer equipment in the coming session. Thank you. Now this is the equipment which is known as power quality analyzer. Power quality analyzer equipment, it is of the Flew company. ठीक है, इसके बटन्स पे ही करिए, जूम आउट कर दो, मतलब पूरा आ जाए मैक्सिमम. Okay, so this is the power quality analyzer equipment designed by Flew. Its number is 435 series 2, and it is power quality and energy analyzer equipment. These are the various buttons which are being provided on this. For example, this is the power button, and this is the power logger button. This is the menu. We will see the function of each and every equipment. Then this is the scope on which we are seeing all the waveforms like voltage sag, voltage swell, etc. Then here we will do the setup for this equipment. Then this is the memory, and then this is save screen options, means if we are getting any measurement, then we can save the screen. So first of all, you can see that we are going to set up. Then here it is setup wizard. Is it visible?
Yes, sir. Sir, यहाँ पर नहीं visible.
Okay. So you can see that we are having different type of configuration. For example, single phase and neutral. then single phase split phase, then three phase star, three phase delta, and then single phase no neutral, three phase open leg. We are having different type of systems, so we can select any system according to our requirement, that we want to select a single phase or three phase. Fine, so we will, for example, if we are selecting uh, this single phase plus neutral, so I will just press enter here. Then this is the supply frequency, which is standardized at 50 Hertz. Then this is the voltage rating, that if we are monitoring any system, then what is the voltage rating of the system. For example, now for a particular system, it is being designed for star at 1000 volt, and for delta it is 173 volt. But we can change it. We can always change it according to our requirement, that what is the voltage requirement of our system. Then we can accordingly change it. And these are the standards, European standards, which are being followed for this equipment. Now this is the ampere range of that equipment. For example, if we are measuring, this equipment is capable of measuring the current up to 6000 amperes. 6000 amperes. So depending upon our requirement, we can fill the value here, over here, that what we want. For example, now it is being selected at 1800 ampere. Fine, so we can always change it at any value given. Fine. And now this is the main screen. So we have set up our system according to our requirement. Now we will see a simple measurement. Now you will see that these are the various types of probes which are being connected here. For example, 1, 2, 3, and 4. These are the current probes. This is 1, 2, 3, 4. These are the current probes, and this is 1, 2, 3, 4, and this is the neutral. These earth, sorry, and these are the voltage probes. So, आशीष पकड़ने से आगे ऐसे रखो. So if we want to connect this current probe, then this is the current probe which we are having. This is the current probe. Fine. This is the point which we are going to connect. Like now it is being connected, and this is the another end of that wire. Fine. So you can see it will open like this. And whatever measurement we want to take, then we will simply enclose it. For example, if we are at this point, for example, we have to take the measurement of that whatever the current is being drawn, then simply we will put it over here. Fine. So through the magnetic field, it will calculate the current, and we can obtain that whatever the current is being drawn over here. Yeah. This is the voltage probe. We can connect it at any point at one end. This is the another end of the probe, and it is being now fixed over here. And now this is the clamp type. So voltage we are measuring through a clamp meter. For example, if we are having any point over here, then we will simply set it like this. Fine. Now we are having this voltage and current. Now these are being projected. Now we'll go to menu. Now you can see we are having various types of parameters. For example, first is the voltage, amperes, hertz, which are being there in the system, then voltage sag and voltage swell, then harmonic, third is the harmonic, then power and energy measurement, then energy loss calculator, then power inverter efficiency. This is particularly designed for solar PV system. Then voltage unbalance, then voltage inrush, then voltage monitoring, voltage flickering, transients, various transients, power wave, and main signaling. So these are the various parameters which we can measure from this equipment. For example, if we want to see the voltage, amperes, and hertz, then we will simply press the enter button over here. And now it will showing us the reading that how much voltage is there, how much current is there. Now it is only a small demo of the load which is being taken. Otherwise, if we are taking properly load of 3 phase, then it will give us the proper measurements. Then this is the main menu. Then we can save the data or we can discard it. Then if we are pressing the save button over here, then we can rename it for any name. For example, for this particular measurement, it is measurement 212, and then we will press OK button. And this is again now the main screen. Now I will show you that how the all the readings which we have taken, how we can see through a software, power log software in the system. We will see. अब इस पे करना सर. This is the power log software. So you can see that all the measurements which I had taken, this is download button. So I can simply press over here and all the measurements will be downloaded over here. Now we are taking any demo reading which we had taken earlier on one of the system. So we are now seeing it. Now you can see that this is the summary. It is giving that where this reading had been taken, when this reading had been taken, and how much is the time duration for this. Measurement summary, you can see that measurement topology was single phase with neutral mode. Then application mode was only for harmonics, you can see. Then first recording it had taken on at 4:05 p.m. and last recording it was for 4:18, means the recording was of 13 minutes. It is just for your reference. Then it is the spreadsheet, means now it is giving us, you can see 4:5:17, 4:5:17, 3:44 millisecond. You can see the accuracy of this equipment, that it is giving us the reading of in the term of milliseconds. Then these are the various voltage and current waveforms which are being drawn. These are the statistics of, for example, you can see that you can calculate VRMS, phase to neutral, you can calculate ARMS current, then fundamental voltage, then fundamental current, then 5 voltage, you can see K factor which we had discussed, THD, if we connect on THD like this, and we can see it for A, then you can see the THD level that it is now going up to 25. These are the number of events which it is being recorded. Now I had now clicked on the harmonics. Now you can see These are the harmonics. For example, for current, now this blue is for voltage, this red is for current, and we can see the minimum and maximum or average value of these harmonics. Here you can see that we are having number of ports, display channels. For example, phase A, then phase B, then phase C. Now these two are, why these two are now being selected? Because we have only chosen only A phase, single phase. Then we are having that neutral mode, then voltage for AB, voltage for BC, voltage for CA, and so on. So we can select any value. If we have selected a proper three-phase system, then all these measurements can be selected and they can be displayed over here. For example, in this particular system, if we are taking the case of only current, then you can see that this is the current harmonic THT which is being given. So you can say this is the THT curve which is there. So you can see that THT is around 40% in this system, 40% and this is the first fundamental current value. Then this is the third harmonic, this is the fifth harmonic, this is the 7th, 9th, 11th and so on. So ultimately we are having a THT value of 40%. Now we have monitored that THT in this system is 40%. So we are having number of tools that we can download the data, then we can save this data, we can export this data to the Excel file, we can print the report out of here. For example, if I am clicking on the print report, then simply the duration from what to what time I had chosen, and then I will simply press the button OK. Any name, let's say 1 2 3. Now this is the report being generated by this equipment. You can see model number, serial number, firmware version. This is the software version of this equipment. Then power log version. Then you can see the general information, if any. Then this is the measurement summary, that the topology was single phase with neutral mode only. Then application mode was only harmonic, because we had studied only harmonic. No voltage sag, no voltage swell. This is the first recording, last recording time period which is being shown over there. The voltage and current limits which are being specified over here. The nominal frequency is 50 Hertz and so on. Now you can see the voltage and current variation for A phase in terms of current. This is for current only. This is the same graph which we had discussed, that you can see that same THT level of 40% we are getting over here, and other harmonics as well. These are the number of events wise calculation of harmonics. For example, the number of events it had conducted, for example 41 and 50, up to 51 events it had conducted, but from 42 to 50 range, and the number of events are almost nil. So the main events are occurring at this 38 and 39 volts. So like in this way we can generate any report from this. We had not connected any proper load to this system. That's why I had shown only the demo version of any reading which I had taken earlier. If we have a proper load, then you can actually see the value of this. So that's all for today. If you are having any questions, then the session is open.
If you have any doubts, you can just ask. Any doubts from any nodal centers? Yeah, they are asking, I think.
Hello.
Yes, we can hear you.
Morning, sir.
Good morning.
We are already gone through the power quality issues on transmission and distribution side. My question is that whether the power quality issues are dependent on how the electricity generated.
Excuse me, sir. Or like what you're telling is not clear. You just leave your mic and go to the near the laptop and you can just speak. Go to the laptop and just speak.
Sir, in this session, we have thoroughly gone through power quality issues on transmission and distribution side. My
Haji.
question is that whether there is a role of power generation issue in power quality.
No, generally all these are mainly on distribution sides, and at transmission levels there are also voltage flicker type problem, but at generation side there is no such problem of power quality, because at generation side we are only getting the main power quality problems are occurring from the load side. Means whenever we are connecting any load to the system, then it will draw any current from the non-linear current from the system, then it will lead to the harmonic value, which will then convert it into the voltage harmonics. So mainly on supply side, there is no such type of problem is there on the generation side.
One more doubt. Yes, it is.
Hello, sir. There is another question.
Hanji.
You are told about that in power quality issues, if the consumers are using the power in domestic purposes, there is a problem of neighboring load. What is that problem? Please explain thoroughly.
Neighboring load simply means that we are having two examples that, for example, there are two customers which are being connected to the same network. Then if one customer is using suppose you can say 5 ACs, air conditioners, and the second customer is only using the fans and lights, then the first customer which is having 5 air conditioners, then these 5 air conditioners are non-linear loads. And because these two customers are being connected to the same network, so all the current harmonics are being traveled at the point of common coupling side from the second from where the second customer is getting the power. Fine. So all these harmonics are now being transferred to the point of common coupling, and from PCC itself now it is being transferred to the second customer. So the second customer has no role in harmonics or any power quality degradation in this case, but he is getting the degradation in power quality due to the first customer, which is at its neighborhood. This was the only point which I was telling.
Okay, thank you, sir.
Thank you.
From any other centers? Here, participants?
So I have one question regarding
इनसे तो बाद में पूछ लेंगे, पहले उनसे पूछेंगे.
No, inside.
Colleges के name
DIT? Do you have any doubts? वैसे ही बैठा है. Next कोई और? ज्ञान ज्योति?
Excuse me, ma'am.
Yes, sir.
I'm a faculty here from the IT University of
Sir, why TDD is preferred over THD, sir, as a harmonics performance parameter?
No, now it is not preferred. These are the various phenomena that is THD and TDD. If we are measuring TDD, talking about TDD, then it is only telling us regarding the demand, that whatever demand is there, then we can take the measurements out of this. We are not preferring one quantity or the other. These are the different values. We are having THD value for general purpose, and we are having TDD for only demand purpose. That is the main difference between the two.
Both are required, I think.
Both are required.
Thank you, sir.
Thank you.
Gyan Jyoti, no? Gyan Jyoti Institute, yeah. Yes, Gyan Jyoti, do you have any doubts?
ये लोकल वाला ही है हमारा ज्ञान ज्योति चंडी मोहाली वाला.
मोहाली है मुझे लग रहा है. मुलाना?
No doubt, ma'am.
Okay. Okay, I think now we have come to the end of the session, and I
ये
just
फर्स्ट लैपटॉप है ना, ये मेरा ईमेल आईडी लिखा है, ये डिस्प्ले कर दीजिए अगर कोई डाउट हुआ.
so like if you have any doubts, you can just contact sir. His email ID is displayed here. He is from Peck University of Technology, Chandigarh. And I first of all thank sir for delivering such a wonderful lecture. I was just online watching from YouTube, and I just came now here. So it was really very wonderful. And I thank you, sir, for coming so long and delivering like your sharing your knowledge. And we have our next expert from Tapar. He's delivering on Homer. He's also ready here. So after a short tea break, we will reassemble here. So now we will break for tea. And we will sharp come at 11:30. So all the centers, please just note it. We will be sharp starting the Homer lecture at 11:30. So we can just break for a tea now. Where are our other participants? They're coming? Sir?
Okay, ma'am. I am leaving.
Okay, sir. Thanks.
ओके सर, मिलते हैं फिर पटियाला में.
हो गया बैठा है लोग आ गया जस्ट वील अनाउंस यस स्टार्टिंग शॉर्टली बोल के यहाँ तो कोई आया नहीं अभी
कोई नहीं, अभी टाइम लगेगा आई थिंक.
2 मिनट छुट्टी हो गई
हाँ
to start shortly. All the nodal centers, please make your participants get seated. We are going to start the session shortly. I request all the nodal centers to make your participants get seated. Yeah, little faster. All right. होमर सॉफ्टवेयर है स्लोली उसका स्क्रीन एंड कहाँ है एक छोटा सा एग्जांपल देख लिया तो भी आप वो बोल रहे हैं कि आफ्टरनून में यू बी शोइंग दी थिंग ना तो वो एक छोटा सा सिंपल से कि ये है फिर उसका बारे में बताने के बाद एक डाल के बिकॉज बहुत ज़्यादा हम फुल दिखा दिया तो भी दे विल गेट कंफ्यूज तो एक सिंपल दिखा Nodal centers, please make your participants get seated fast. So, very good afternoon to one and all. So now we have come on the second session of 11th, the fourth day. And today, now we have with us Mr. Shakti Singh. He is assistant professor in the Thapar University in the electrical engineering department, electrical and instrumentation engineering department. And he is an expert in Homer software. So we have him with us. And I just hand over the session to Dr. Shakti Singh. Sir, you can just continue.
थैंक यू मैम, थैंक यू वेरी मच.
आप वहाँ बोलते समय थोड़ा लाउडर बोलना पड़ेगा because mic is here. Then only it's lit.
Okay. Okay. Good morning, everybody. You can hear? Yes. Okay. The Homer software is, see, the first thing is what exactly Homer is and what we can do with the help of Homer. First thing is. So I will just explain one circuit and suppose we have a load, right? And we want to load demand. We have some electricity load, right? And we want to fulfill this load demand. We want to meet this demand, meet the demand with the help of some renewable energy sources, right? So first thing is how I choose which renewable energy sources I'm going to use first, right? Suppose we have a 20 kilowatt load per day. Per day, peak load is 20 kilowatt, and kWh we can find out very easily. So suppose I have a load curve like this. This is any load curve we have with respect to time, and this is load demand, right? So the first thing is, suppose I want to meet the total load demand by any renewable sources. The first thing is how I will choose the renewable sources. That will depend upon geographical locations. Suppose I want to install a PV system. First thing, right? Suppose I want to start a PV system, and so the only thing main thing which required I required is capacity of PV system. See. This is simply I am using solar photovoltaic panels to meet this load demand. So this system is not feasible kind of system because every time you cannot meet the demand. Suppose you have a 24-hour data and you have a solar panel system. So this panel is going to generate according to the solar radiation, right? So what will happen when there is no radiation? First thing. Another thing is, let's say suppose the load is AC load. So again there is one problem. We cannot meet this demand because this is AC and this we are generating DC. So one problem is that. Now the second thing is how much PV, how much capacity of PV I require to meet this demand. My question is how we are going to find out how much capacity, how much kilowatt panel, how much rating panel we are going to install at this area where this load demand is. Here. So the first thing I required is I required a say let's say I'm using this is so this is demand again and I'm using let's say this is AC load, right? So first I need a converter. See, this is AC bus, this is DC bus, right? We will generate DC, we will convert it into AC, and we will feed to the load, or we will meet the load requirement. We are going to see total demand we are going to meet by the PV system. Now this system is not reliable. Why? Because there is no backup system, right? So what we are going to do is in this system, in this hybrid system. So again, suppose I use a battery. Right? I'm using a battery. Now what will happen? When I have excess of electricity, I'm going to store in battery, right? When there is a deficiency in say electricity, I'm going to use battery. And the circuit will be like battery is DC. Why I put to and fro arrow, dual arrow, because we can charge and we can discharge. And I put this on a DC bus. So there is no need of converter because these all are generating DC only, right? So now the point is this battery, when there is deficiency of power, we are going to take power from the battery. And another thing is when we have excess of power, we are going to charge the battery. So charging and discharging of battery is one concept. Now the point is how I am going to select the sizes of component. Suppose I have a 20 kilowatt peak load and I have some load curve, any load curve which is that depends upon say this is summer, this is say let's say winter, this is daytime, nighttime, any load graph is available to us. According to that load graph, how much capacity I am going to? That is one big question. So I need to design the system in such a way that all the demand is met. First thing. Second thing is I require the system to be optimized. Second big thing is that second biggest question. Second important question is this system is economical or not? Right. Suppose somebody want to put a wind turbine also in this system. So let's say I am going to put a wind turbine. And this is AC wind turbine or DC wind turbine, that depends upon the availability of the wind turbine. So this is directly we can feed to the load. And excess power is generating from wind turbine, we can convert it into DC, and we have a dual converter, AC to DC and DC to AC, and we can feed to the battery. Suppose you want to put a small hydro system. Right? So So here again I'm going to put it on AC bus. So again, what will be the capacity of small hydro? Suppose you want to you have, this is called standalone system. We are not connected to the grid, right? We are not connected to the grid. Suppose we have excess power and we want to connect it to the grid. Again, if I'm not using any backup, so I can connect grid in a dual mode, right? I can take power from the grid, I can give power to the grid. So how this system works basically, how we design this system, that is all about this Homer software. Next question is this system is optimized? Optimized in terms of cost analysis. And at the end, what we are looking for the cost is, we are looking for the cost of energy. How much is the, say, let's say 5 rupees per kWh, 10 rupees per kWh, 15 rupees kWh, or 1 rupees per kWh. So how we are going to find out the cost analysis. So now, see, if I'm using this system, alone system, I'm not using any wind turbine, I'm not using any grid, I'm not using any small hydro system, I'm just using a simply PV system, right? Simply PV and battery. So first thing I will do in today's class, how to find out the size of these panels, first thing. And second thing, we are going to find out what will be the cost of the system. And also we are going to check the reliability of the system. Again, suppose if I introduce a wind turbine in this system, so what will be effect on the system? How cost is affected, first thing, and how the size of wind turbine is selected. So we need basically, and again, the last demo of the day will be if I have all this standalone system and I want to work it into, I want say grid connection also. So how grid connection is going to help you? How the rate of charge from electricity from grid, that sensitive analysis is what we call in Homer system. So let's say I put a small hydro and I put a here biomass, small biomass system. I can put so many systems, fuel cells, like whatever system you are. See, in Punjab we used to have enough plenty of biomass, so we can use biomass system. In your Jammu and Kashmir, let's say you have a very resources for small hydro, you can use. In Gujarat and Rajasthan, we have very good of say PV system, Madhya Pradesh. So that depends upon location to location. In coastal area, there is enough wind is there. So first thing will be how we are going to select the component. So this software tells us what is the capacity of the first thing, what is the capacity of the system. We are going to start to feed the load to meet that load demand, first thing, and what will be the cost of analysis. Suppose I choose all the component in a system, and again I want to say make a comparison. If solar is economical, right? Wind is economical, and finally biomass is economical. Suppose I also need say a backup. If I am not using grid, so I can use a DG, right? So DG will be one say this system is why I am using DG is diesel generator. Now the reliability of system is increased. There is, let's say there are the times when we increase the size of this PV and all this battery, the cost will obviously goes up. So we need to optimize the system. So this software basically gives us optimization or optimal value of components. What we are going to find out in next 1 hour. How DZ is going to work? First thing, we have provisions in software that I want to, let's say we have a load like this and I want to use DZ here only. So we have facilities that I want to use DZ here only. Scheduling is what we call it. And here I want to feed this power from battery and let's say, sorry, battery and PV only. So how much electricity is generated, how much resources are available, how we are going to choose a wind turbine, the capacity of the wind turbine, the number of battery, how we are going to say find out this bus size, all this technical data also we can find out with the help of this commerce software, right? Any doubt, please? Right. So I'm going to design 3 systems. Basically, one with PV plus battery. Again, I am going to introduce some another technology, wind, and finally with DC and biomass or any technology you want me to introduce. We will solve some uh, some case study I will take, right? Okay. Any doubt, please?
No, sir.
So basically, why we need new models? Because we need to expand the grid, right? And we are looking for alternative options like renewable systems we are using. Solar photovoltaic and wind home system, they are most frequent use, and biomass is another, and say small hydro is also like where we have resources. And another thing which is coming up very say in nowadays, that is in fashion, which is called hybrid power system. Hybrid power system is like we are going to mix more than one kind of resources and we are going to meet the load demand. The advantage of any two, we can say if I mix like PV I am using and I am going to put some wind turbine is there, that system is called hybrid system. And it may be a standalone system, it may be a grid connected system, that depends upon what are the applications of system. So in this system, we can see there are so many hybrid system we can use like wind, PV, biomass, fuel cells, small hydros, batteries, how we are going to optimize the system. So I'm going to optimize this system. I'm going to take one system and we'll go to. So what exactly Homer is? So Homer is basically a software which is software tool, I rather say it, that is hybrid optimization model for electric renewable. And this was designed by NREL, USA, and nowadays almost more than 1 lakh people are using this software. And this is one best part is that it has a free version. You can download it from a site and you can start working. You can design your own models. So this is a tool for comparing and evaluating micro power technology option for a wide range of applications, such like suppose village power system. Suppose you have a locality, you have a off-grid location, right? And you have plenty of resources available you, like near to hill station, any hill station, you have a very small village and you want to feed power, you want to meet the load demand. Then say how you have plenty of small hydro options available with you. You have plenty of solar radiation available with you. You have plenty of wind resources available with you. So you can design your own system. So this has very flexibility. You can give the load and you can design according to your system. And the only thing which is missing in this Homer software is that we cannot go to the electrical side of the system. Like what is P value, what is Q value, what is that is one problem. Here this is basically economical aspect we are looking for. We are looking for only the cost of electricity. Suppose you put a small hydro plant, you put a PV system. So we are not going in the detail of like what will be the PU harmonic analysis, all that power system and power quality issues. We cannot deal with this system. We cannot deal with Homer system. I will tell you this. Suppose I want to this room I have, and I want to feed all the power from solar photovoltaic panel. So what will be the capacity of solar power, solar photovoltaic plant? That only I can tell you. But on the bus, what is going on? What is real power? What is say reactive power? What is say anything we cannot tell you. Only cost analysis we do with this, with the help of this one. This is one drawback of this system. So you can design your standalone application, like suppose in your colleges, suppose you're in home, you want to apply a solar photovoltaic, you want to feed power from any source, you can. Grid connected system, there is a facility of grid connection also. In grid connection, like we take electricity from grid and we feed excess electricity to the grid. Like there is recently in Punjab, we have a scheme that is called rooftop solar photovoltaic scheme, where we put some capacities sort of photovoltaic panel on our houses, and that is dual metering system is in that system is there. Suppose I am in day I am generating power and I am not at my home, so the power I feed to the grid, right? When I come back, there is no solar radiation, so I can take that power from the grid, or I can take money from the grid. Both options are available. I can give number of unit to in a day to the grid, and again I can take it back from the grid, right? Or either I can take money, I can charge this much is the amount I have given to you. You adjust that part into my bill. So both options are available, unit to unit or money to money. So conventional technology, few conventional technology also is still available, like diesel generator is available in this. So wherever a backup is required, I can use a diesel generator. And all this diesel generator power coefficient, and how much diesel power, how much diesel we are going to use, how much capacity, again we can do that part. New technology, some new technology. I will give you how many technology we have in this software. So who can use it? First thing, everybody can use it. Suppose you want to design your own system, you are free to use it. You are not supposed to take any permission from anyone. This is a free version and you can download it from website and you can start working on Homer software. Where and possibly why do we use Homer system? See, suppose you want to make a standalone system for your own locality, so you can design your own system. What potential it have? Again, the limitation I am saying is that it is not on the power system side. So it has a potential that maybe in future, in coming year, they are enhancing the say quality of this software. Maybe in few years you will got that all power quality issues and all the small parts also you can add. So what can it do? It can design a system that is optimal. First thing, that optimal in terms of cost analysis, optimal in terms of money analysis. How much if I'm going to put this photovoltaic with battery? Obviously, these things now drawback with all this renewable energy system like PV and all. The only factor is which is hindering the use of these technologies, basically cost. The cost is still out of reach. Means, suppose I want to design this system, the cost of photovoltaic battery and this load and converter, that will come say even more than 10 rupees per kilowatt, something like that. So that is one problem. If I'm going to use wind, obviously cost will be down. So that depend upon the. So how does it work? I'm going to tell you, and how to use it. We have a long session for. Now, what are the questions Homer can answer? Should I buy a wind turbine, PV array, or both? Suppose I want to feed this, I want to meet this load demand. I want to install a system in my home where I have a load. So PV will be economical, or wind will be economical, or both will be economical. This is we are going to do with the help of, right? Why I am saying like that? Wind is economical and PV. Let's say you don't have plenty of wind resources available at your location. You have very poor wind speed. Then wind will be mostly, say, in terms of it will be costly, because to operate a turbine we need a fixed amount of wind speed. And suppose you are going to put that wind turbine in this room, then this is totally wastage of money. So will my design meet growing demand? Whatever demand I have, say I have to meet total demand by renewable sources, and there will be some times in standalone system the drawback I must say that we cannot meet all demand. Sometime it happens, because suppose I put a 5 kilowatt panel somewhere, so it is going to the output varies with respect to time. So what will happen? if I want to meet all the demand, I need to have a storage system. Suppose sometime there is not continuously there is no sun for 10 days, let's say one example. So that means I need to have a capacity bank of 10 days if I'm using the standalone system. But once you have designed the system, we design the system according to the whole year data, but we have never predicted that there will be no 10 days sun. What we do is most of the time we see the previous data. Suppose I want to put a solar photovoltaic panel at NITTTR Chandigarh. So what I'm going to see is I'm going to see the past solar radiation pattern or solar wind resource pattern from the past years. I cannot predict the future. Let's say 10 days there is no sun. In that case, I need a large battery bank. But I have calculated the battery bank according to the previous data, right? So that is one question. So capacity shortage will be one critical issue, and there will be some time when let's say you have a less load and your battery is full and you have plenty of energy with you. Then what you are going to do with that energy, right? So in that case, we can have a deferrable load also. That I want to pump the water from the ground, and it is not required at a particular time. Whenever I have excess of electricity, I'm using it. Suppose I want to use it as a heat energy or thermal energy, whatever. But that if you have enough, we can use. If you don't have enough, we cannot use. So deferrable load will be also there in this system. And in that case, suppose you don't have a deferrable load, then the power will be wastage. Your battery is full, your demand is met, power is wastage. In that case, you have excess electricity. So what you are going to do with that excess electricity? Because at the end, the cost of electricity will be the money spent divided by say the only two factors: the money you spend and the energy you generate. But if you are generating excess energy, we are not paying for it. We will pay according to the load only, because our load demand is like how much kWh per day is the demand. I'm going to give you the bill according to the demand only. If you are generating so much of excess electricity, I'm not going to pay you. That is one problem. Suppose you have designed a system and solar radiation, yeah, any parameter changes. So what will happen? Suppose I put a DC in this system, and all of a sudden tomorrow, right, the price of diesel change. Like every day we have a news in evening that diesel is cut down by 2 rupees, or petrol is cut down by 1 rupees, or they are costly by 1 rupees, 2 rupees, something like that. So obviously my cost of electricity is going to be affected, right? So how much it's going to be effective? So we have a sensitivity analysis in that system. If price is this 1 rupees, price is 2 rupees, what will be the cost? So I will design that system according to the sensitivity analysis also. If price change, if solar radiation change, if wind average change, so many parameters, if cost change, so I can feed so many parameters to this. So what is the price of, at the end, Homer will tell us, this is the capacity we are supposed to store, first thing, and this is the price of electricity that you have generated from this system, right? How should I operate my system? Again, I can tell to the Homer, like I have given you one example. I want to feed this complete load by renewable only. I don't want to use DC. So I'm going to put all power from PV generation. Yeah, next thing is, suppose I have a diesel generator and I want to use it in daytime, right? And I have a solar photovoltaic system and I want to use diesel in day due to pollution and any effect, say noise pollution, whatever it may be. So at that time we have excess electricity, we are going to store it, and when DC is not available, solar photovoltaic not available, we are going to take it back from the batteries, right? So I can fix the schedule also. Suppose 2 hour in like weekdays we have a high load, right? So what will happen in that case? If you are going to fix one system, other system is flexible to you. If you are going to fix one system, rest of the demand you have to feed by the other system. That is one part, right? So how should I operate my system? That will up to me. There are few changes I can make in the system. So what basically Homer do is it estimate the cost and determine the feasibility of system design over the 8760 hour in a year. So what we are going to do in this software, in this Homer, in system, we are going to take 1 year data, complete data, like resources data, like load demand, and we are going to find out number of units, and we are going to find out also what will be the cost of electricity that is available for us. So basically it optimizes the system. It simulate each system configuration. There are so many number of say combinations that will coming out from this system. Let's say this system. There I can see that there are three systems in this standalone system. One is I can meet this demand by PV plus battery. Size will be different. Agree. Second option is PV plus diesel is one option. If I'm not going to use batteries, second choice, right? Third choice will be PV plus diesel plus battery, and fourth choice will be diesel plus battery, right? So these are the four options I have. And sometime suppose I am using DC only, so I don't need a converter that is connected to the AC bus only. So DC obviously cost will be more. If I'm meeting the all load electricity demand from DC only, the cost factor will be one issue. I'm going to use DC plus battery, again I can use it. DC plus battery plus PV, again I can use it. So many options I can. So it simulates all the options to you, and it rank them according to the cost of electricity. Suppose in this system PV plus DC only is a better choice. We don't need a large battery backup. Whenever PV is not there, I'm going to operate diesel system. So it may be that it is a economical system. DC plus battery, it may be one of the economical options. So it simulates all say possible combinations, and according to the cost of combination, it finally give you the results that this is the best system. Now it's up to me that I'm looking for the more say economical option, or I'm looking for the more reliable option. It is not going to tell us that this is a reliable system, right? Suppose PV system plus battery plus DC is most reliable system in this case, right? And I'm not supposed to even design it. If I have a 20 kilowatt of peak load, so I'm going to put just a generator of 20 kilowatt. That is one solution, right? Then if I have a PV 10 kilowatt in a day, so I can reduce the size of DC, right? So this is what we are going to find out, size and all that part. And so it configure every possible combination, and it tell us that this is the feasible solution and this is most economical solution. Now it's up to us which solution we opt, right? It sorted all this optimization system by net present cost. That net present cost means cost of electricity. Somewhere it is related. Net present cost of the system and cost of electricity that will come out from the total system. Sensitive analysis, like perform an optimization for each sensitivity variable. That let's say I have given you one example. Suppose tomorrow the fuel cost is changed. So obviously that comes under the sensitivity analysis. So next day my cost of now the beauty of this software is you just feed the sensitive analysis and something happen in future. So you know that if price changes, my cost of electricity tomorrow will be 10 rupees. So this is the beauty of this software. So next day my cost of now the beauty of this software is you just feed the sensitive analysis and something happen in future. So you know that if price changes, my cost of electricity tomorrow will be 5 rupees per unit or 5.1 rupees per unit. You're not supposed to adjust the thing every time. You just feed the values and you will get all the sensitive analysis. So this is again already I told you that this is designed by NRL, and this is from last 20 years. This is commercially available, and in up to 2009 it has 1 lakh users, and it has been downloaded more than 2-3 lakhs time from that site, and it is freely available. You can and this is one of the best, or you can say what's leading microgrid modeling software. You can design your own microgrid system. It uses both conventional and renewable energy technique. In conventional, it has some limitations. It uses most of the time diesels only, and battery is also conventional. It is intended to evaluate design option for both off-grid and grid-connected power system for remote, standalone, and distributed generation application. Previously, there was no option for grid connectivity and also grid extension. In like 2007 or 8, when I was using it, there was no chance for, if suppose I want to connect this system to grid, there was no like that. In 2009-8, they introduced this concept. Suppose I have excess power, I'm going to feed it to the grid, and grid connection mode is, you know what grid connection mode is. So this you can, first thing is how to download it. You can download it from two websites. One is that is NRL, that is from USA, National Renewable Energy Laboratory. You can download it from their website, or we have a separately website for Homer, that is www.homerenergy.com. You can download any of the options. One is that is free, that is Homer Beta or Homer Legacy is the name for routine software, and nowadays they have Homer Pro, which is advanced version of what you say Homer, and it is, but the problem with this advanced version, that is it is only for a trial version. That is that gave you a free 1 month trial, and again suppose you want to extend, there is no provision, you have to buy that software. But in case of Homer Beta, there is not such a thing. After every 3 months you have to just update your software, and just you need to fill a survey form, and that is totally free of cost. But Homer Pro is not free of cost. That is available for only 1 month, and only a slight differences are there between Homer Pro and Homer. So you can use Homer, there is no problem. Every 3 months you have to just update your data, and that is totally, you can download student version, you can download. If you want to download professional, you need to pay some dollars. So paid is available throughout, and paid may there is no concept of registering again and again and again downloading. That kind of thing is not available. You can be a lifetime member and so many, but little fees is required in dollars. So it's up to you which method you are going to opt. But most of the people, they use Homer Beta Legacy version. You can download it freely and you can use. In 3 months you can do a little exercise, and that will be again available to you. You need to get a password, and again you can say. So these are the components where this Homer have: solar photovoltaic panels, wind turbines, runoff river hydropower, right? Generators. Generators may a variety of generators is available according to the fuel: diesel, gasoline, biogas, alternative, custom fuels, co-fired. Biomass generator is there nowadays. They introduce biomass generator in this. And again, option is electric utility grid. Connected to the grid is also connected to the grid, or off grid. You can, grid extension is also there. Suppose you want you want to install this system at a distance of you want to meet this load demand at a distance of 5 kilometers from grid. So that cost also we can calculate. Okay, how much wires we require, how much transformer, everything we can do that part. And the latest thing is they introduce in this Homer is micro turbine and fuel cell. Fuel cell is the latest addition in this. Storage, there is two method of storage in Homer. One is battery bank and another is hydrogen tank. Nowadays in Homer Pro you can find that they have put even flywheels also, right? Load, you can give any load day to day, and variability in load also. If you can feed 876-hour load according to your demand. Deferrable load, I already discussed that you have excess of electricity, you can go for say water pumping or heat application. Thermal applications is, there are so many load options when we will come to the actual system. So you can download so many publications and so many resource material from various website also. In last, I remember, in last almost 10 years, there are more than hundreds publication in such good reputed journals like Elsewhere, Taylor Francis, IEEE. They are using Homer only. I will give you the few. I will show you some few applications, few case studies where they have applied Homer and they have calculated the cost analysis. So there is a good say scope for research if you are looking for the publication side also. Some input files also supplied by some particular website. Suppose you want to take a solar resource data for particular site. So NASA is providing you free of cost data. You can download hourly data for wind speed, humidity, temperature, say solar radiation at a particular site. You are just supposed to feed some coordinates and you will get one zip file where you have all 8760-hour data available with you, right? So according to that data, we are going to use Homer software because every time we need data, previous data, current data we don't have, right? Current data means only I can have today's solar radiation or wind speed data, but tomorrow I cannot predict. So what we do, we find a site where say there is a good amount of resources available. I'm not going to put say a small hydropower plant in Punjab at Patiala or Chandigarh because we don't have enough renewable options available. So you can go in Kashmir and you can go to Himachal, Uttarakhand, where you can put small hydro data. So every data is available freely at various websites. You can Google it and you can find out. Some meteorological sites are there. Even in your phone, you can find out what is exactly temperature this time, what is humidity this time, what is solar radiation at this time, what is wind speed at this time. You can find out so many data from website. So this Homer is going to tell us what will be the size of PV array. Obviously, we discussed how much is the kilowatt size we required, the number of wind turbines if we are using some say hybrid system, the presence of hydro system. Again, I'm going to find out the size of hydro system, small hydro system. Suppose see what we are. Suppose I have a 100 kilowatt load, and I want to feed it. I want to meet the all demand by small hydro system, right? So what will be the capacity required? It's not like 100 to 100. The efficiency of the system obviously will. Suppose I have a 1 kilowatt solar photovoltaic panel. So at standard condition, the rating value is 1 kilowatt. But if solar radiation is like half of the full solar radiation, so it's going to generate half, right? So that depends upon how much resources we have. Suppose you don't have plenty of water available for small hydro plant, then what you are going to use? We are going to use backup system, and we are going to see reserve, what you call in power system. We are going to have some capacity reserve. Suppose I have a load of 20 kilowatt and I have a DC of say 30 kilowatt. I am keeping it this 10 reserve. So that depend upon what kind of system you want to. Size of each generator, diesel generator. So number of batteries, how much battery we required, and life of battery, and see so many factors will be there. Suppose you design a system for 20 years, let's say. The lifetime of system is 20 years, right? So what will happen is solar photovoltaic panel, they have a life of 20 years. Agree? What about the battery life?
4 years.
3 to 4 years. So how we are going to accommodate that part, that every 4 year or 5 year we are going to replace the battery? So obviously that will make that will need some money. And once you design a system for 20 years, you have to tell us that these are the replacements I required in 20 years. Let's say you are saying that a battery life is 4 years, let's say. So how many replacement have we required? At least five request replacement. And again, that replacement, the problem is that if I purchase a battery of one battery today at the cost of 10,000 rupees, let's say, right? After 5 year, I'm going to replace it. Let's say 4 year or 5 year is the battery life. So at the end means after 4 year, what will be the cost of the battery?
Will be higher.
Yes, it will be higher. So I'm going to include that higher part into my calculation today, right? So I'm going to use that current value of money and past value of money and present value of future value of the money in my system. Suppose I buy a battery today at a cost of 10,000 rupees. At the end of the project life, what will be the value of 10,000? Right? So I have to take all money back from the customer only. I will include the interest also. If I'm investing 1 lakh rupees in a system and I'm doing it for 20 years, so what I will charge the interest? Obviously, I will charge the interest if I'm investing 1 lakh rupees, and after that I'm going to calculate the cost of energy. And in the meantime, suppose 5 replacement is required, so I'm going to calculate that value. After today's battery cost is 10,000, and after 4 year battery cost will be, let's say, 15,000. And what will be the value of 15,000 in terms of today? What I'm going to recover, that I'm going to recover all it from the customer only. I will say 5 rupees is the cost. 5 rupees, like for an example, you have a hydro plant. You have fuel input free. So what is the current money charging? The only you are supposed to give salary to the workers, and your maintenance cost, yes. But why the cost of electricity is too high? Because we have included that infrastructure and capital cost in that. Yes. That's why it's too high. Otherwise, so it should be free almost. Nowadays, it should be free. If we don't consider the capital cost, we are not paying for any input. Yes, only maintenance and few people working on this. It is almost free, but it is not free because we have invested so much amount, and we are taking interest with interest back from the customer, right? So, what will be the size? Obviously, AC to DC and DC to AC. It depends upon system. Suppose I'm going to use this DC load, right? My load is DC, so converter is not required. If I'm not using DC, I'm using DC load, so converter is not required. So what I have said is converter money. Size of converter I have saved, money in terms of converter I have saved. So that depends upon the system. Suppose I have all AC system, all AC generation. I have a DC and I have a wind turbine. So I don't require a DC bus. I don't have battery. I don't require a DC bus. So it depends upon what kind of application you are looking for. So the dispatch strategy means how we are going to meet the load demand. What is our priority? Our priority is to fulfill all the demand, or it may be sometime that I have a 20 kilowatt say demand, and sometime 1 kilowatt remain say attended. So it's up to me. But I want that every time 20 kilowatt should be met first. My priority is. So in that case, I need to go for the upper side. Upper side means ratings will be obviously high, right? But still, we have say few drawbacks of Homer. One is that this is totally black. This is one drawback with all software systems. That is, they are all black box approaches. Black box approaches means we don't know what exactly is happening inside the system, how they are going to calculate the value. We just feed the data, we say run, right, and it gives us the optimized value. But how it has optimized the system, what technique they have used to optimize system. So it's a conventional, it's a artificial evolutionary algorithm, it's a, say, some another programming is there. They don't tell us. And sometimes it happens that see, the advantage of these software tools, disadvantage of this software tool is that our conventional method, suppose I do a mathematical modeling of the system and I find out the optimal size by using any method. Let's say I'm using genetic algorithm, let's say, for an example. Sometimes it happens, sometimes most of the time it happens that these are existing technologies, existing algorithm, they provide you the better result, right? But in that case, you need to, say, design a mathematical model for that system. You need to calculate according to the solar input. You need to first calculate the PV output. You need to calculate the wind output, wind turbine output according to the wind speed or wind height or wind turbine. Again, you are going to optimize the system. In that case, you need to do physical things. And even in optimization also, we have some optimization tools, right, where we can feed. Again, the concept is there. So, suppose we have a genetic algorithm toolbox. So I'm going to just give the value and that will give us the result. But still we know that this is genetic algorithm tool. But when you are going to apply yourself, you are not using any tool, you are supposed to design a mathematical model. So what we do in research is we take a help of Homer and we find out the optimal sizing of this say hybrid system, and we compare it with the another technology. So there are so many papers available on this, that somebody put a Homer and in the same system we put a conventional, non-conventional means evolutionary algorithm are coming up. So many genetic, PSO, ABC, artificial bee colony, ant colony, harmony search. So many algorithms are nowadays available. So we can apply that also. And if you found better results than this, we can compare that this conventional technique or non-conventional technique is better. But it's still base we take as a homework. Also. Or if you want to compare between the technology, also that part we can do. Suppose PSO gives some different result and genetic algorithm gives some different results. So there will be some. This is This is not the final answer for the optimization system. There is no limit at all. All the day, say every day, some new technology is coming up, and they say these results are better than the previous technology. Some changes they are doing in algorithm, so they are saying this is a good algorithm. So again, single function minimization is one problem. You cannot minimize multi optimization problem. We cannot solve with the homework. Like you want to minimize the cost, and also you want to minimize the. Suppose I am using this diesel generator concept, right? So obviously diesel generator have some pollutant emissions, CO2 and all that part, right? So we can do only one optimization. Suppose I want to minimize diesel use. I want to use diesel rarely. When it's the last time means critical situation are there, I am going to use 11th hour, right? So that time I want to use diesel. So dual multi-optimization is not there in this system. Multi-optimization means we cannot minimize cost simultaneously environmental issues, pollutions. So that is one problem. In that case, you need to go for the multi-object optimization. Required more computational time as compared to existing optimization technique. This is another factor. When your system grows means the size of system is large. Let's say you put electric two kind of electric load, 10 type of system, battery bank, and 50 times 50 sensitivity analysis, right? And size of the system you want to start from interval of 1 kilowatt, 2 kilowatt, 3 kilowatt up to 100 kilowatt system is big, large load is there, then there is one problem with this system. It takes hours to calculate the value. Even sometime it run all day. You just calculate, run it and forget it. It will take like 5 or 6 hours, 10 hours, that depends. And for very small application, it do hardly in 2 minutes, 1 minute. But in case of optimization technique, they don't take so much time, right? As compared to Homer, they are they give very fast response. Genetic algorithm, all these technology, you just model it and just run it on your own PC, say whatever the processor you are having. It takes 1 by 10, let's say, time of one problem, same problem. So they are very fast. And another issue is that it doesn't consider intra-hour variability. Means we have a time step of 1 hour, like 8760 hour data is there. Suppose now in this 1 hour load is changing, so we don't have that kind of facility available with us. Even in optimization technique, we generally use time step 1 hour. Most of the time in all, say, electrical system, when we talk about load, yeah, load curve, right? Yeah, load demand, whatever. So you have seen most of the time we use 1 hour interval, 24 hour. When we talk about solar radiation, we take a data of 24 hour, and 1 hour is standard time reference. Between the 1 hour, there is 60 minutes, and every minute load or solar radiation can be changed. So that will be a very complex problem. So delta is 1 hour. So how to create, how to use Homer is, first thing, after the lunch, I'm going to give you the live how we take data, how we feed data, and how we say optimize the system. So these are few slides I just want to show, so that next time your software tools, when we are going to use software tools, things will be look familiar to you. So we start a new Homer file like this. This file I am going to show you somewhere. So equipment to consider is, first thing, now it's up to you what model you want to design. First thing, add and remove is one button there. I will show you the screen. First, let me show you the screen. This is one say new screen. This is totally blank screen, right? We just downloaded it from NRL website or any website. Now it's free to use, right? So this is the first screen, project 1, right? So first thing is, that thing that come to my mind is for which location I am going to design a system, and what are the sources I am going to use. First, it's up to you. Suppose you have a small hydro available with you. You are going to use it with small hydro. You have fuel cell available with you, and solar available with you, wind, biomass, or generator. So first thing is, and the second thing is, what kind of load we are going to use. Like if we have DC load, system will be this. Sorry, AC load system will be this one. If we have a DC load, we don't need converter, right? We are not using DC, so we don't need a converter. So same bus pay here, same load will be on the same bus, system on the same bus, battery on the same bus. Nothing is required. If we have AC and DC, then things are a little bit complicated. Because some are generating AC, some are generating DC. So every time we need a converter, and we use a dual converter, AC to DC and DC. And also the rating of converter is also one issue, right? Suppose you have this AC load and you all 20 kilowatt is load, so at least you need a 20 kilowatt converter into efficiency of the converter. Let's say it will be more than let's say 80%, 90%. So size of the converter will be greater than the load demand. Suppose you have DC available with you and you want to feed a 20 kilowatt of AC. So size of converter will be obviously greater than 22. greater than 20, right? So this is the first screen I'm going to show you, and here I'm going to use add. These are the options available with us. You can see I'm just naming them. Primary load 2 kind of load I can manage. Primary load means, let's say I have two separate units, means one is community load, one is household load, right? One is factory load, one is household load. And in also in load also we have so many different kind of load, like weekend load. I'm just taking one load, right? Just load. This is what we got on a screen, primary load, right? So I'm just taking any load. So when you just click on this load, a screen pop up, right? Now it's up to you how much load you want to give it. So I'm just giving you some little, say, if you have a word file with you, 8760 hour data with you have with you can import that file also in this software.
Word file or Excel file?
Word file.
Word file.
Word file. Right? Let's say you have a particular site and you know the every hour load data. So you can import it from here. Import file. That file you have that is in your computer somewhere. So when you click on it, and you can find out where or you want to enter manually. Let's say I'm just giving some load profile tools, right? So at the first hour, I have a 1 kilowatt load, right? Second hour, 2 kilowatt, 3 kilowatt, 4 kilowatt, 5 kilowatt, 5 at the sixth, seventh at 5. All of a sudden, 8 o'clock, it increases, 6 kilowatt. In day, it increases. It goes up increasing 9, 10, 12, and it goes up to peak of 14 kilowatt, right? And again, it slow down, let's say, on the reducing side. Whatever the data you have with you, you can give it to it. 3, 4, whatever the curve, shape of the curve you can see from, say, this I am doing manually. You can feed your own file also, right? So this is the daily load profile. You can see in first slide. You can analyze it. This is 1 day. This is month January. I've given it weekdays profile, right? Suppose in weekends pay, there is slight variation in load, right? So I can, let's say, the peak hour is not as much as high as in terms of say weekdays, like, right? Whatever the curve is. See, this is, I have given 2 days data to it. One is in January. On weekend days, different load is there, and on weekdays, different load is there. This is like I'm saying it winter profile. And in summers,
Sir, we have to make two load curves different, or
yes, we can up to so many. You can feed, let's say, 365 load curve you can feed. In Word file, so you will have every day.
we are doing for week and for 5 days.
This is general waveform I am giving. I'm not feeding any Word file, right? Like this is a load profile in January, right? And let's say in June, load is double. Let's say 2, 4, 4, 4, or 45. Let's say the peak load. See, something like that, right? And again in June we have 2 variations. One is weekdays, another is weekend. So here you can see that I have given it average. Here you can see in average window that average kilowatt is 170 and average kilowatt is 7 in this particular June. Let's say January total. This is one complete year's average, and peak load is 54. So I have given in June, you see 54. Can you see 54? See here at 10 to 11 I have given it 54. So this is my peak load. So I have to design system according to the peak load, because at any moment we have to feed this 54 kilowatts. From where I am going to feed it, that is up to my application. I am going to feed it by solar panel, wind turbine, or something like batteries with the help, some battery, some wind, whatever. That is up to you, how you want to make your system, right? And again, this is all I have given fixed load, right? Suppose you want to make a variation in load. Let's say I say that every day 10% variation is load is in there. Yes. Now it generates a file of 8760 hours, where from previous day it take automatically 10% variation, right? And again I can say, suppose I want to now you have given it load profile, like so many things we do in Excel. Suppose this is the load profile. Suppose you want to use in your Microsoft Word, you want to use this graph. So how you are going to use this graph? I have given you are going to fit into first Word Excel, Microsoft Excel, and then you are going to plot the curve. Suppose you want to say use your this data in your Word file. So there is no need. Here also you can say copy file, this file, copy meta file, right? Directly it copies. See meta file. Yes, I'm just going to the paint and I'm just going to paint. See, right? So you can use this file. Now you can convert this file into any file. JPG, PNG, whatever required, you can require it. Say any file save as, you just go to save as and you can find PNG picture, and you see this figure is what you call is looking more handsome than Excel file. Yes, right? So you can use that part. Even suppose you want to use this data also. So just go to right click. You can save. You can copy bitmap image. You can copy meta file. You want to save it as PNG file. You can save as meta file. Directly you can save it. Right. You can save any name. Suppose you want to export this data to your.
Excuse me, sir.
Yes, sir.
Sorry to interrupt you, sir. The random variability where you mentioned day-to-day variation of 10%.
Yes, sir.
Is it taken 10% on the higher side or 5% higher side and 5% lower side? Could you please explain that?
It will be. I will show you the curve also. I will give you the data. You can see yourself also. I will tell you how to see that part. Right.
Okay. 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 Thank you.
I will show you the exactly data for one complete year. Don't worry, sir.
Okay.
Right, sir?
Thank you, sir. Sure. Thank you.
So point is, suppose I want to see here in second figure you can see January, February, March, April, May. I have taken winter profile. Right. In 4 months, I am just going to use like June, July, August, September, October, November. I am going to use, let's say, summer profile. And day-to-day variation will be there. I will show you how to take out that data. You will see that it varies 10% positive to say every day. How it varies, you can see that part. Suppose you don't want to, you want to stick to your own data. Let's say you have a 876 hour data and you want to say use your own data, and there is no need of variation. So most of the time what we do is we take our original data. When we have to design a system, we design system according to our own data. Suppose what is the actual kilowatt is available, what is the day-to-day profile that we take from 8760. We will do that part later on. We will see what is exactly data is. You can see from here you can plot the data. See, this window is coming out from plot. Now you can see, sir. See here. This is load data for complete year, right? Variation is there. Load data for complete year. Now you can call this data in your any file. What you have to do is like January data is there, February data is there, March, April, and summer data is there. Now we are going to see how it's going to vary the data. So what I am going to do is, again, I can save this file in any format, MATLAB. I want to see this data. I want to export this data. So this will be original data. Let's say I'm exporting it on. This is load data, right? So there will be a file that will be say generated on my desktop. Load data. See, right? So this is the data for 876 hours. See,
So it's a word file, sir.
this is a word file, right? This is a word file. This is 876 hour 0 data. This is complete data, right? This is 8760 hour data, and that will be depend upon. See, I have given it, I think, variability, 10% variabilities I have given it here. See, this is scale data, 1.163 data is there, baseline data, load data, 2.36 is there, 3.9, and I have given it the variability. See, 111, 6.97, next is 8 point something, variability I have given it to. If you are not giving it variability, the data will be fixed to you. Whatever data you see, you can take this data from your word file, right? Suppose you have a 8760 hours data in your word file. You want to design your own system. No variability is there. See, this is variable. I have given it variability. If I'm not giving it any variability, it will be fixed. See, all data will be fixed. See, I have to run first it. Okay. Okay. Two profile I have given, I think. Yes. What we did is, see, now there is no load variability. The load demand on very 1st January is same. On 2nd January, yes. 3rd, again same. 4th, again same. 5th, again same. 6th, it is changed. Why? Yes. Suppose now I want to see on which side it's going to 10%, right? Variabilities I have given. So again I can see it's going to up or down. That depends upon both sides. It can give plus minus. So variability is up to us. So we generally take our own data and we design system according to the data. We normally even don't change the, see, when we increase the number of variables, the time optimization time increase basically. Now we have to design this system according to 4 load graph. One is for winter, weekdays, weekend, right? One is for summers, weekdays, winter. So basically these are 4 problems, and peak load will be same. Peak load will be like I have given it say 54 peak. So peak, uh, let's say this peak happen in one day in June. So the problem is with this system, with this optimization system is that we have to consider that 54 for one day also. And according to that, if we want to meet that all demand, 54, and let's say the variation in load is one day the load demand is 54, and routine or what average demand is 7 only. Now see the difference. We have to design the system according to the 54. And if you're designing system according to the 54, so many say kWh is going to be wastage because we will have excess electricity, right? And here we can scale annual average kilowatt per day. I can change it again. Sensitivity analysis will be there. Suppose I want to see the data for 180, 190 scale average. Uh, Scale baseline average is 170. So I can change so many parameters. I can export this file to anywhere. See, suppose now you have any doubt how it calculates thing. First thing is, suppose how we calculate average, how we calculate kilowatt peak, load factor, how it calculate, how it day-to-day variation, random variability, it generate, how to all these, any doubt on this screen, suppose you have. So we go to the help side. We just click on the help. See. Now in help side, uh, you will find so many things. Suppose you want to find some data from any particular. Suppose you want to test your system on a standard microgrid. Standard microgrid means suppose you want to see how exactly power is. What is the cost analysis for a standard? We have so many standard test grid data, microgrid data. Like we have a Santa Rica jail in USA that is called to be one of the best microgrid system in the world. And there they have solar panel, wind turbine, and fuel cell system. Totally independent standalone system. So you want to use that load data, and you want to make change in your system. You want to see that load according to that load you are going to put one say, like we have when we talk about power system, we have some standard system like IEEE bus system. But here in microgrid, we don't have such systems. You are the sole owner of your own microgrid. So your microgrid is feasible, reliable, economical. Who is going to tell us? Suppose you want to you have a IEEE bus system and you want to feed some distribution generation in there. So you are going to compare something. But now the problem is in power system you have existing, established, proven systems. We are going to modify them. But in microgrid we don't have such kind of system. That is one say drawback. And let's say they have data for USA site, and I'm going to deal with the same data here. So there will be variability in data. So that is one problem with the standalone system. Our own system, own data, everything we are on. Solely owner of microgrid system. So my point is, if suppose I design this system, I'm going to verify that part, that this is perfect, or this is okay, or this is reliable. That is one thing. How I'm going to say that this is the load and this is the PV that fits this system best? How I'm going to say that this is the best system? Because this is not a standard system. This is not a IEEE bus system or something like that. This is not a scaled system. So that is one system. So we feed the data, we take it, and so there is no comparison at all. Suppose you pick any case study from any location, for any location from any paper, but you will not get all data. But in case of IEEE bus system, you will got all the data. At this bus, you have this P, you have Q, you have everything, you can get it. But in that case, there is nothing like. So in that case, you design system according to your demand also. And authenticity of the system is that one big issue, that it is okay or not. We can see every time what is power generated. We can see all the data. We can analyze all the data. Like we have a 20 kilowatt load, and I put a, let's say, 50 kilowatt solar panel. So I can see at that this hour this panel is generating this much of amount, and this is the amount stored in battery. This is the electricity stored in battery. This is the wind turbine generating right now. I can see the whole data, right? But authenticity is nothing, because they are not standard data. Standard data it cannot be in a microgrid. You cannot have a standard data because they are designed according to their geographical locations. The same value, the same load, same resources, they are not going to provide us. and we need so much of data for analysis. So that is one. Now you see, finding data to run Homer is, these are the few websites you can find out solar radiation data, monthly solar radiation, wind speed, everything, wind speed data. You can find it out from so many sites. NASA is providing you free of cost, say all data, all 876-hour data, right? So here you can find out. Here you can type what we are looking for. Anything, say solar. Just type any word. How, say state of charge, whatever you have any query, you just type here and you will load variability I'm looking for. See, load data. See how we calculate load factor. So there is a help in system where you can find out whatever query to you is. See, I have given you the load factor. See here, load factor is 0.131. So how we calculate load factor? See here, if you have an average load of 66 and the peak load is 10.5, the load factor is simply 2.5 divided by 0.26. So these all play a role in load factor. That's what I'm telling you. We have a peak of 54 and we have a average of 7. So load factor will be, say, different. So load factor is going to play a role, right? What other factor was we were looking for? The variability, right? Random variability. So you can find out how it's going to vary the load. This is solar data. Can you find out any word here? Random variability. No. So we can see it from there how it's going to vary load is variable. We can see it from the data only. 10% what we were talking about. Suppose I am giving it 10%. So I can plot it again. Now see. We can see it for 2 days and we can find out how it's going to be vary. Time to time step or 10%. See, now I'm going to just zoom it a little bit. Now you see. Yes. Previously I have fixed the data. No load variation is I have given to it. So now it's see. Now your answer is it can go up. I think for both in both directions. See 10%. See here, right? It goes down, it goes up. So 10% is.
Excuse me, sir.
Yes, sir.
So could you show me this the data for these 3 days with 10% and without 10% adjustment?
Okay. What we have given time to time step date. We have given random variability day to day 10%, right?
Now, if you could reduce it to 0 and then compare the two graphs, if that can be done.
Yes, sir. This is the data I got from 3 days. So let's see what it do, what Homer do, right? So this is the scale data 1.66 on very first day, right? Can you see that part?
Yes, I can.
1.166, 2.223. This is scale data 4.4348, and this is 10%. I think. No. This is it is taking. Okay. Yes. This is taking. The next data is 0.904. Yes, sir. Can you get it?
Yes, sir, I can hear you.
The first data was 1.166,
Okay.
and next day the data is 0.904.
So what I am asking you is that with the random variable set to 10%, each and every what do you say, the each and every data for each and every time, is it varied by 10% or is
Yes.
it varied by 5% in the positive side, 5% in the negative side? That is my question, sir.
It is 1 hour data at the see at on January 1st, 1 hour pay data is 1.166, and January 2 pay data is 0.904, right? Right? There is no plus and minus, and in on next say January 3rd, the data is 1.086 of previous day data. See, just note down three values: 1.166, and another value is 0.904, and third value is 1.086. Now you can calculate how it's varying, right?
Okay, okay, sir.
Okay, you can calculate. There will be 10% variation will be there, right?
Okay, so every month that for that particular
Not,
date there will
not
be a
every month. Not every month. Every day it's going to vary your load 10%.
okay for every day. Fine.
Yes, it sometime it's up, sometime it's down. Variability means plus or minus both, right?
Okay.
In
Okay.
one
Thank you,
side,
sir.
so it's going to increasing every time. If I'm going to increase load every day 10%, so load will be increase every time. See, so annual scale down, say average, we have to maintain. So that's why variability is there. But you are not supposed to take it variable data, because we are working on our own system. So we are going to feed this data basically, right? We are going to take a data from any location, any power plant, any wherever, any distribution center, whatever it may be. So we are going to give personally or a word file to this system. Now you see, January 1, January 2 down, January 3 again down, 4 again. See, all variable is there. See, now you see the graph. And when I'm now, you just see, when I'm not going to give any variability to the load curve will be something like state. I'm not giving it any variability. See, now I'm going to plot it. See, they all are same, right? See here, January 1st, January 2. See, I'm not varying any load. Whatever load I have given to it, it has taken a scale data, and everyday load is same. See, January 3rd load is same, January 4 load is same, and we have given it. See, weekend days different load. So January 5 and January 6 load is different, and you see January 7 again we have given the same load, and January 8 see again, right? We have made these changes. We have given it 4 load. One is summer load on weekdays, on weekend days, and winter load on weekdays and winter days. Suppose I want to make it variable. Why I need to make it variable? First thing is, suppose I don't want to show one single graph to you. So let it be do some exercise that variability can be there. And I know that it can goes up to, suppose I have a load curve. So I know my load curve. Chronological data will be there. So I know that this load is going to be very only 10% or 20%, or it can be very 50%. So that in that case, system will be different, right? So it's up to you how you are going to use that load part, right? So again, you can export this data and you can plot again. Same story is there. You can call this in a Word file. Suppose you want to use in your Excel file somewhere. You want to plot this data. You want to you directly you can use pictures also from here, right? That's up to you. See, you can use both options. You can copy this file and you can say export this data to any Word file. That's up to you, right? So it's all about what kind of system you want to design. Suppose you want to keep load demand constant throughout the year. See how it looks like now. January. Now let's say in June, I just want to use the same load. So every time this curve, June, July, August, they will be the same. I don't want to be my load to be variable. I have a fixed schedule of that this is the load and I want to design a system this way. So you can calculate it. You want to change any sensitivity analysis, you efficiency input, you whatever. See, you want to give it to load factor you want, and see another is DC load. Suppose now when you click to the DC, it becomes a DC load. Now I will design system. DC bus will be different. See, if I'm taking now, you see this is changed. This screen is changed. This is now DC load, right? This is 170 kilowatt hour per day का load है, peak है 54. No variability is there, nothing is there. Only I just want to design my system according to this DC load. See, right? So next part is what I want to, how I want to meet this load. What I am going to apply. Suppose I want to, first I will take the example of solar photovoltaic, right? Okay.
I think we can break for lunch if it is next. Then after lunch we have बाद शुरू कर सकते हैं.
Okay.
So now I think we will break for lunch, and afternoon also we have this Homer software. So sharp 2:15 we will reassemble. Okay, so all of you 2:15 the session will start again. So I just want all of you to come back at 2:15. The same session will start, and if you have any doubts you can just clear it that time. So this session will again start at 2:15. So now we'll break for lunch and we will reassemble at 2:15.
Thank you.
हाँ जी फोटो ले आइए वो वीडियो कॉल लेके आ वीडियो फोटो ले आया इधर भी फोटो ले आया इधर देख लिया अब वो रोटी खाना खा रहा है चल नहीं पड़ा है अभी देखें दोनों के दो बार बांट के मैं अमित का खाना खाए 5 मिनट वो एक बार मैं एक बार याद है मैं शुरू में आया नया नया था तो लिख लिख के लेके
2 बजे बजिए कैबिनेट है ये भी है जेब में तो लगा फोन कोई ले गया होगा तो यहाँ बड़ा टाइम हो जाएगा अगर प्रतीक के पास होगा वो कौन सा रूम नंबर है 10
वो देख लेगा में काम जा रहे हैं कि कूलर अगर हम गवर्नमेंट में तो अप्रूव हो जाती है तो फिर यहाँ पे कर रहा हूँ अगर मेरा कितने की जरूरत है बट वही की जरूरत है तो उसके क्या फायदा होगा ये तो ना कि हर एक रूम के अंदर एक यूजर करो अब मतलब मैं जोड़ दिए वीडियो दो वीडियो तीन कट हम ये सारे 6 मिनट ये दो एक बंदे में कैसे नब्बे साढ़े सात में ही मौत हो जाती है जल्दी वो चलने वाला उसमें पूरा अगर बिल्कुल गर्म पानी में वही पानी टैंकी वाला पानी कुछ रात को दो तीन बढ़ जाता है गर्म गर्म सा पानी टैंकी में रहता है बच्चों से नहाने आ जाते हैं हाँ हाँ कोई चीज़ में क्या मतलब कुछ भी नहीं है 80 लीटर पानी अच्छा
मैं ऐसे अनाउंस कर लेती हूँ उसको ऑन अभी हो गया Nodal centers, please make your participants get seated. We are going to start shortly. All the nodal centers, make your participants get seated. हाँ 4 o'clock.
लेट होएगा थोड़ा तो
हाँ थोड़ा 10-15 मिनट्स हो गया तो कुछ प्रॉब्लम नहीं है बट वो ना मोस्ट ऑफ द कॉलेजेस प्राइवेट है ना तो उनका प्रॉब्लम है कि 4 o'clock उनका खत्म हो जाता है हमारा तो 5:30 तक है नो प्रॉब्लम सो दे विल फाइंड इट डिफिकल्ट हाँ बिकॉज उनका बसेस वाला भी 4:15 4:30 सो मोस्टली 4 o'clock आप खत्म करने के लिए
ठीक है
So I think they are also coming. Please make your participants get seated. All the nodal centers. We will be continuing with the morning session on Homer itself. So sir is here. All the nodal centers, you can make your participants get seated. तो एक्चुअली यही प्रॉब्लम होता है कि दे डोंट सिट कंटिन्यूअसली लाइक बीच बीच में आके बैठ के फिर बोलते हैं कि हमको कुछ समझ में नहीं आ रहा So now let us start the session. I think most of the nodal centers they have made their participants get seated. So now let us start with this session on Homer. Okay, sir.
Thank you and welcome back. So far we have decided that we are going to have a DC system or AC system, right? So we have collected all the data required for the load, right? So this was the load, and let's say I'm just making it simple, and I'm just putting it like peak is not 54. I just want to make it somewhere like where is 54? Huh? Where we have given 54? Where? Okay, let's leave it. So this is the load we have taken, and let's say I have taken DC load, so things will be different, right? Now the second thing is how I am going to what source I am looking for. The first thing is, right? So the first, let's say I'm going to meet this all load demand by solar photovoltaic panels. So I'm going to put one PV, right? So PV is not connected because we are not given any data, not resource, nothing like that. So here, once you just click on this, now you are supposed to give the cost analysis of PV. First thing, like suppose one kilowatt PV cost you all cost will be in dollars only, right? No Indian rupee, no euro, nothing like that. All money value will be in dollars only. Suppose you purchase a 1 kilowatt solar panel for, let's say, $1,000, right? And replacement cost obviously the same. And you want to change the replacement cost, let's say 800, you want to keep it. Operational and maintenance cost, let's say $1 per year, yeah, $5 per year. It's up to you how you manage the cost. Now size to consider is 1 kilowatt. That is up to you how much size you are going to give it to. If we want to put a cap on size, we will find out another source. That will be the maximum value of. Let's say that will decide according to the load. Let's say 50 kilowatt is a peak, right? So I'm going to just give it random size number 2, 3, 4. The more is the number, more is the optimization parameters, right? 6, 7, 10, 15, 20, 25, 30, 35, 40, 45, 50, something like 55, 60, 100, whatever the number I am giving. If you are giving in increasing order, these are the number. This is basically a variable. From all of these given data, he will select the best for you, right? So this is, let's say, 65 and 70 or something like that. Now, again, this is DC, right? So solar photovoltaic is DC. Here you can change every value. Lifetime is, let's say, 20 years, and you think that something is 10 year, so you can change. Even you can change the sensitive analysis. Suppose lifetime is 30 years, so you can give this data 40 years, let's say. So it will simulate for 20 also, and for 40 also different system, for 50 also, whatever the value you give, it will simulate differently, right? Derating factor is one constant, that is something like efficiency of constant for solar photovoltaic panel. I will tell you the formula how we got derating factor. Slope degree, how you are going to put your solar photovoltaic panel, what slope you are going to give it from the horizontal, azimuthal degree, whatever the, see, locations, west, south, ground, say reflectance, whatever values, let's say tracking system. This is advanced system, right? Suppose you want to put a tracking system, so you can adjust power according to the movement of the sun, right? So if you are not giving any, you are not applying any tracking system, it will give you fixed value. No power will be changed. Power will be changed according to the solar radiation only, right? So it has some mathematical equations from where it calculates the thing. Let's say consider effect of temperature. When you calculate solar photovoltaic power, we take consider major two factor is involved. One is temperature outside, one is radiation, solar radiation. So if you want to take effect of temperature, or if you don't want to take effect of temperature, you can remove it from here. And how solar panel calculate power, see, we can go to the help. See, this all help is available here. Derating factor, what is derating factor? You can click and you can find out derating factor. Does Homer account for the effect of temperature? Yes. If you say yes, now the best part is in some book you will find that there are hundreds of equations to calculate the power of solar photovoltaic panel from solar radiation. How Homer calculate power? So Homer calculate power, you can click to this and there is one formula. I will come to this formula later on. This is how solar photovoltaic power is calculated. Here there are four major parameter. One is rated capacity of PV array, YPV, that is its power output under STC condition. Suppose you are taking 1 kilowatt power, it can generate 1 kilowatt maximum, its rated value. In according to, and derating factor is what we give 80%, let's say wastage in atmospheric conditions or electrical or whatever, 80% is derating factor. GT is the solar radiation incident on PV array, right? GT-STC standard test condition, that is 1 kilowatt per meter square. So the idea of solar power generation is, if you have 1 kilowatt per meter square solar radiation at a particular solar panel, then it can generate 1 kilowatt panel is there and it can generate 1 kilowatt. And if you have a derating factor of 100%, if derating factor is 80% and you have solar radiation 1 kilowatt per meter square, it can give you 1 kilowatt. We don't consider area in this. 1 kilowatt is radiation is there, we just calculate the power according to the formula. Alpha T is temperature coefficient of power, TC is PV cell temperature, TC-STC is standard test conditions. And finally, if you are not considering any effect of temperature, the very simple formula, very say easy formula to calculate power is PPV equals to YPV FPV GT GTSC. So simple formula. GT is solar radiation. Its rating will be kilowatt per meter square. Let's say you have half solar radiation, right? So half, GT is half and GT is 1. The GT bar is half and GT bar STC is 1. And let's say 1 kilowatt panel is there, 1 kilowatt and 80% derating factor is there. So 1 into 0.8 into half divided by 1 is the power generated at any particular site, right? If you are taking effective temperature, we are going to use this formula, the upper one plus alpha p Tc minus Tcr Tc. So as like solar photovoltaic panel, we are going to find out power, all different powers like wind turbine, thermal, sorry, diesel generator power and small hydro power. So we have equations for that. Like in small hydro, we have waterfall, height of the all these parameters. So you can find out from here how small hydro. You just type here small hydro and everything whatever related to C, you will go to everything, right? You can go to help site and you can find out how power is generated. See what is head count, what is say hydro head, every data you can find out it. How see effective head, all these data. This is for a small hydro. In case of wind, you can find out see, right? See wind data, right? Wind data. Everything is there. See wind speed. So every mathematical equation is available with the help, right? So now, so far what we did is we have put a let's say up to 70 kilowatt panel maximum. This is maximum value of solar photovoltaic panel I am providing to homer. Let's say system is not feasible, so it will give me some warning that this is not a feasible solution. Please add some more photovoltaic or some battery, something like that, right? So once you have decided the solar for photo, now you can add, let's say you want to add some battery. So I can go for battery. And here you can find three features, three main features on this screen. One is do not model grid, right? System is connected to grid and compare standalone system grid extension. These are three different case studies we can do with this honor. Do not model grid means this is a standalone system. We are not connected this to the grid. When you click on system is connected to grid, grid window will pop up and you have to feed the data, right? I will show you how grid connected system is going to work. Compare standalone system to grid extension. When we are talking about grid extension, we are going to compare the cost. Standalone is better or we should extend the grid to that particular location. So any three system we can do. So I'm doing first do not model grid. I'm not connected this system to the grid. So I'm just say adding the battery. Clear? Now when I click to the battery, there is again this window come up. Now we have to provide the battery input, right? First thing is here there are so many inbuilt battery specification in there, right? When you click on any specification, you will find details of that battery. This is the chart of that battery. This is data sheet of that particular battery. Even some website is also given to you that see this is a Trojan L16P battery, right? You can find out how much ampere hour is there, how much voltage is there, round trip efficiency is 85%, right? But the problem is that you cannot change anything. This is an inbuilt system, right? Suppose you want to build your own battery, you can start with like say new battery, right? So you can give this data. Let's say you design a battery and that has 100% efficiency, right? So here you can give, you have a battery that is 1360 ampere hour capacity. That is local battery, you can say. But if you have some standard battery, just take the data and just feed it, right? See, so these are the few parameters which you can see. So what basically we need in that case is, again, we are looking for the cost. And now you see this is, I have taken Trojan L16P, right? So this is a battery, 6-volt battery, 360 ampere hour, 2.61 kWh, right? When I multiplied with 6, this is 2.16 kWh. Lifetime throughout is kWh. Now I will decide the battery per string. I will decide the bus voltage side, right? Let's say I take just battery per string, 6-volt one battery hai. I'm just taking 20. So bus voltage will be 120 volt. So there will be battery per string 20. So 20 into 2, sorry, 20 into 6, 120 ka bus ho gaya. Bus voltage. Bus voltage is 120. This is the only factor where we talk about the bus voltage. In one string there will be 20 batteries. So if I choose a different battery, let's say that is this one. This is a 2 volt battery, but ampere hour is very high. See, 2500 ampere hour is there. So I will take again now 20 battery. This the bus voltage is only 40. Right. So agar if I want to make a bus voltage of 120, 60 battery I need. So it's up to me how much I am going to use. See, I'm just taking it. Now minimum battery life, again that was a sensitive factor. What is the minimum battery life? 4. Let's say I'm saying 3 to 4. And see, I can go it for like floating battery life also. Floating battery life means what we say is 3 or 4 year is a rough number. Suppose we use it proper, we maintain every condition for the battery. It can go to up to 10 years. There is no problem. जो specifications हैं, if we keep that in limits, the life of battery can be increased. It's not like that every 4 year you have to dump your battery. It's not like that. It may be that its life is 6 years, 7 years sometime, and sometime even less than 4 years. If there is some damage, then it can be go beyond say 4 years also. So it's up to you how you choose floating life. It can be 10 years if you maintain the charging rate and discharging rate in level, and you maintain the SOC state of charge of the battery within the limit. Let's say I say that battery should never go beyond 30% of its final value. Let's say one example. That means 30% charge it has to be there every time. Suppose you take out total power from the battery. Again you start from the zero. So the life of the battery will say change in that case. So we have to maintain that limit. And here I have mentioned you the limit. See details. Minimum state of charge 30%. That means this battery will not go down beyond 30%. Maximum it can 70% it can discharge only, right? And it cannot be charged above 100%. Obviously that is SOC maximum. And you can even fix SOC maximum also. Let's say you want to charge up to 80%. You don't want to be charged a battery fully. Then you can change the limits, right? So again, I have to give some money value. So let's say one capital cost of the battery. It's up to you from where you purchase and what is the cost. Operating and maintenance, जो भी. Size, how much you want to give? 1 string, 2 string, 3 string, 4 string, 5, 6, 7, 8, 9, 10. That means 10 into 20. We can have maximum 200 batteries, right? Number of batteries we can have 200. And what one battery cost us 1 into 200. Yes, any doubt is there? Okay. So number of battery we can increase. Let's say 12, 14, 15, 18, 20, 25, 300, whatever the maximum. Let's say you want to fix number of battery, right? Let's say I can have maximum 300 batteries. I want to keep battery minimum. So if you want to keep battery minimum, you have to go voltage limit high, plus you have to need more say PV install capacity will be increased, or you need to put backup. And suppose you want to only PV and battery only, then limit will be there. Let's say I'm just putting it 1000. Let it be decided. Let's say it will give you me the value, final value. You just go and you just put this much of kilowatt of panel, and these are the number of batteries you put.
That means these are the batteries we can afford that we are specifying over here.
Yes, this up to you. Suppose
so that is not final.
No, that's see optimization is what you every time in optimization what we do is we fix a maximum value all the time. Otherwise, so there is no limit.
Okay.
Right? Once like you want to optimize two parameters x and y. So you will tell na, where your x and y lies. 0 to 100, x lies, and y lies 0 to 100. So optimization value will be between 100 and 100. Else you don't fix the values, it will be always minimum to 0.
Yes.
Right? If you want to minimize any equation, answer will be x equals to 0, y equals to 0, say minimum value, right? So maximum 100, 100 to 100, what is the optimization value? That is some constraint is there. So let's say you want to give any random value to the batteries, that I can afford any battery. See, number of battery increase, the cost will increase.
Yes.
Both are say contradicted. Contradicted. Number of battery increase, cost increase. So we are going to minimize the thing. So, and sometimes system is not feasible, so don't worry, it will give you some warning that the system is not feasible. Either you increase the size of battery, either you put a backup, you increase the size of photovoltaic, or reduce the load. It will say something like that. So we have put this, right? And this is AC load, and photovoltaic is DC, right? Battery is DC. You can see the both way, two-way around. Battery power can be stored, and now system is not connected. There is one gap is inside the system. The load is not connected to the supply. This is called symmetric diagram, what I have already built in on Blackboard. System is not connected. There is no power flow. So what we do is we need a converter, right? Because we are generating DC, and we are now, you see the interesting part. If I just change this load into DC, everything will be okay. See here, no need of converter. PV is generating DC, battery is storing DC, load is DC. So directly PV to DC, battery to DC, two-way switch is there, two-way connection communication is there with the battery, PV one way, load one way, right? But you see, I cannot model it to the grid. Grid I cannot feed DC, right? So I need a converter. Let's get back to the AC load, right? So what I need is, I need a converter, right? Until unless you don't fix up the parameter, it will not be connected. Now see, I have not given anything. So I will take a size of 1, and let's say the cost is 100 per kilowatt again. Operating cost is 1, whatever it may be. Lifetime. Here at this window, I can put more and more sensitive analysis. Let's say, what happen if inverter life is 20 years? What happen if inverter life is 25 years? Right? Suppose 15 years is fixed. What happen if inverter is, we have a different inverter that goes up to 20 years? Same value, same.
More possibilities can be.
Yes. Number of more. See, these are number of variables. You are giving more and more variables to the system. So obviously, system will be complicated. And it gives me the result on 15, on 20, and 25. It will give me the 3 different results. On 15, the cost will be this. If lifetime is 20, what will happen? What will be the factor in this case? The cost will change. See why cost will change. If you have a lifetime of solar photovoltaic 20 years, right? And you have a lifetime of inverter converter 15 years. So that means
Inverter needs to be
replaced, right? Inverter need to be replaced after 15 years. One more thing. After you have taken life of inverter 15 years, and your project life is like 20 years. So what will happen to the rest of 10 years of inverter? You will get a salvage value also. After 20 years, project will be finished. So what you are going to be do with that inverter, which has a life of 10 years still remaining within? We are going to resell it. We are going to find out salvage value of money. If I purchase one thing in 10,000, according to salvage concept, I purchase a car in 5 lakh. So its value is, let's say, 10% decreasing every year. So after 10 years, its value will be 10, that kind of year. So salvage value will be there on each and every component, right? Like battery. If I have a project life of 10 years, and battery life I have given 4 years. So what will happen to the 2 year? So we are going to resell that part. That is called salvage value of the system. So salvage value in everything that it consider totally. Again, you can go to the help site if you have any problem. You can click on the help button and you can find out what exactly you are looking for, right? Now you see efficiency is 90%. Rectifier input, we are using dual, right? AC to DC and DC to AC, both way. So rectifier efficiency I can give, inverter efficiency I can give. In both way efficiency will be different, or it can be same. It depends upon you how you are taking. When you convert DC into AC, things will be different. AC into DC, let's say efficiency is different. So that's up to you how you take. Again, size accordingly. I just give a random number. I just take the peak load demand and I just give the number. When we model system in grid mode, we have a different concept for inverter size, right? So I'm just giving it some values, 3, 4, whatever the values. I will not take the exactly 4, right? 50, 100. The more of the variables you give size to consider, the more complex becomes system, because it has to find out your answer from these data only, right? So calculation time will increase if you keep the steps like 10, 20, 30, 40, 50, let's say. So it will select from all these 5 sizes, right? And if you give 50 like 1, 2, 3, 4, 5, so it has now 50 variables with this. So it will take more time, but it will do, right? And accuracy will be, in that case, it will be more because it will give you the perfect result, right? But time taken will be more. In that case, you simulate. Now you see this system is connected. This is a complete system, right? Now the point is, we have not provided any resource data to the system. We have taken the load, that is up to us. What is the load, DC, AC? Now we have not feed any resource data. Suppose I put this system in USA, in India, in China. So how it's going to be work differently. So the thing is, first, and interest rate and all these things. So these are the resources data. You can see just below it, and here you can see, you can give your name, author name, like your name, and you can write some data. See notes also, so that you remember what you have done. Here you can write some notes that this is the demo program or whatever. You can write any story, whatever stories is like, right. So now the point is that I have not feed any data. How this panel will generate? I know the formula, and in that formula I need only one thing, that is radiation, solar radiation. Temperature I am not taking. Let's say if I am taking temperature, consider effect of temperature, I have to give temperature data also on each hour. What is solar radiation, what is temperature, right? In case of wind turbine, what is wind speed, what is whatever height of the everything, right? So in that case, economics, first I will do the economics. Annual real interest rate, this is the interest rate. We all do all calculation with the interest rate. We consider this is a must value, 6%, 8%, whatever the rate is. That is up to your system. Let's say कि your आपका interest rate is in India 8% है, and government has provided you subsidy. So interest rate is, let's say, it become 4%, right? So interest rate is up to you, but there will be some interest rate. Without interest rate, we cannot go for financial calculations. If I am investing 1 lakh in 20 years, what is the value of 1 lakh? I have to consider. Without interest rate, there is nothing like financial calculations we can do. Otherwise, life will be so simple. 1 lakh invested and power generated, so simple. Cost of electricity, right? But it's not like that. Every time component, value of money, inflations, project lifetime. See, 25 year I have taken. So what we do, we match the things. See here, project lifetime I have taken 25 year. Solar photovoltaic life I have taken 20 years only, right? Battery life I have taken 4 years, right? Inverter life I have taken 15 years. So I will adjust the things. Let's say I am taking project life 20 years. Now, one thing is clear, there is no replacement for solar photovoltaic panel, right? 5 replacement for battery, because I have fixed the value. 1 replacement for inverter. So I will calculate all this money, that after 4 years this battery's amount is this, inverter and salvage value will have also. Inflation is there. Let's say some fixed cost is there system, which is not included in component cost. Let's say you need to build a platform and you need $10,000 for this, because these all costs we have given is just like component cost. We purchase a solar photovoltaic, we don't include the installation cost in that, right? Suppose I want to put it on my roof, so there will be some, let's say 20,000 rupees I require, right? Labor charges and all that. I purchase from a website. They are not going to store storage. And I'm going to put a wind turbine or small hydro. Capital cost is required. You need to whatever. Operating cost, system fixed cost. Suppose you want to have 4 workers, 4 labor, right? Their cost is required. Recruitment cost, whatever. Maintenance cost, whatever. Capacity shortage. Let's say penalty. Let's say your load is not met and you want to put a penalty on the system. Let's say you have a peak load of 55 and sometime your load is not met and 54 is generated. So 1 kilowatt, you want to put a penalty on any, let's say I want to put a 1000 penalty, my load doesn't match. So all these issues we can address. If you don't put penalty, it will go freely. So simple. If you put a penalty, that means you are giving this software a constraint. We have to take care about this also. If something goes wrong in the system, we need to pay a penalty of this much, right? Now the point is, this economics part we can do, right? We can feed whatever. System control, let's say simulation time, step minutes. Let's say 120 मैं 2 hours के लिए करता हूँ, but below that it doesn't do that part. Load following, cyclic following, what you want to say, it's up to you how you system you want to give priority to any system. You want to say cycling following load, you want to have multiple generators, you want to have 2 type of wind turbine, these kind of all parameters are there. Temperature I have taken, right? Now the point is how we feed resources. So I just click on solar resources. Now this is again that load kind of thing come up. Yes. Now what I am looking for is how much solar radiation is available at my site. What is solar radiation available? And you know the graph. Graph will be increase peak time and it will be decrease. It will be something sinusoidal, half cycle of sinusoidal kind of graph, right? And though there is no solar radiation, like in it will be like a curve, right? So how to find out data first? So there is so many methods to find out data. Again, you can directly find out data from internet. If you are connected to internet, get data via internet, right? So you are supposed to give latitude and longitude of your location, right? Suppose Chandigarh is, you just do one thing, you just select your site, right? And you just find out the coordinate of the site. Very easily you can find out coordinates like Chandigarh. You just type Chandigarh in Wikipedia and you will find coordinates of Chandigarh. That Chandigarh is situated at this longitude, north to south, and very easily you can find the coordinate. So you just feed the coordinates, whatever it may be, 272, whatever exactly coordinate is there, right? Or simply you can find out it from time zone also. Like we are in India, so GMT plus 5. This is any data, right? Any rough number data. You want a particular space location data, you just feed the coordinate, right? And if you want any data from any site, some inbuilt data is there in this. See, almost every country's data is there. Central Africa, see all this, Canada and all that, Afghanistan, Pakistan, sub India. See, so you can get the data. One thing. Other thing is you just give it a again manually, right? You have a Word file and you want to import your data, and let's say January May I have a 5 kilowatt per meter square per day average solar radiation in my space. In February, let's say again 6, again in March it goes increasing 8, 9, 10, like July also 10, August a little down, September let's say again down, October 7, 5 and 4, let's say. So this is site specific data. This is clearness index. Clearness index is how sunny day is, right? How clear the day is. So when you are connected to the internet, that is very easy. You just take the data from solar radiation from any site. Even if you go to the NASA site, they will provide you a zip file. In that you just feed the data. They have 10 to 15 year data available with them, and you just give them dates, coordinates also, obviously coordinates and dates, that from July to this year to this year they will you give a, there is some system, right?
Sir, here only 1 year data is required.
1 year. We are going to simulate it for only 1 year.
If we want to simulate it for last, let us say I want to take the data for last 10 years.
No, it will simulate for 1 year.
Only 1 year.
Only 1 year, right? Because in that case you are supposed to give more and more data. Things will be more complicated. Because what we do is, see, the point is, when we talk about cost of electricity, first thing, right? We take that how much money we have spent in a year and how much electricity is generated. That is one concept. Suppose you have a different data, 10-year data. So there will be 10 simulations. Every year, according to your data, the cost of electricity will be different. It doesn't do that part. See, you have one data set available with you for 1 year. Cost of electricity will be different, right? Next year, cost of electricity will be different because your resource data is different. Third year, cost of electricity will be different. So there is no limit for that. You can go up to 50 cost of electricity. There is no provision such like. So it simulates only for 1 year, right? Any year, you just take the data and you just feed the data, and it will give you the cost of electricity, right? And we all do this for one year also. We calculate cost of energy for 1 year. Even within the system, we calculate even for months, but it will do for 1 year. Throughout the year, that will be the charges for electricity, right? So again, scaled annual average, see 6.97, whatever I have given, and here also you can change. Suppose 8 is the average, 9 is the average. In these windows, you are giving more and more variable to the system. Suppose data is 11, data is 12, 13, something like that. So more are the windows, more are the system say going to take the time. Now you see. Again, we can do the same exercise also. Suppose you want to use this graph in your paper somewhere. So again, you can copy, and suppose you want to take this data, export data. See, again, you want to plot the data. See. So this will take data from, if I have selected this data GMT plus, this will take the standard data. So again, you can plot this data. You see. Now you see. Right, I have taken a standard data, GMT data, 5.3 India ka data. This is for solar radiation. Right. This is like January we have less, February. You can see, you can sense it from graph.
For a country, not for a state.
Not from a state. Yeah. Not state, for your location where you are sitting.
We are sending the coordinates to them.
Yes, they will give you the data. हमारे
Exact coordinates.
exact
Chandigarh
coordinate. You just feed the coordinate of this room, and you will got 1 year data from internet. Homer is directly connected to that site, right? They will give you the data. Wind, temperature, solar resources, everything they will give. Right? And again, you can do the same thing here also. Here you can export data. See, suppose you want to use this data somewhere in your MATLAB file, let's say. So you need this data. You have taken the data, you have not done anything. Say, suppose I want to take this data in my MATLAB file somewhere. I want to use this data, right? So I will save this data. This is, let's say, PV data. Sorry, radiation data. I can save it again. Now see what happened in this file. See, every time these values are 0, right? Because there is no solar radiation. You can see the curve, na? Increasing, 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 and again, see, 24-hour curve is there. And here you can see in hour also 1 day data. See, any date. See, you can see. See, this is July 3rd data. Time is 0 to 6. No solar radiation is there, right? It goes up. Yeah. Color is okay. Color I cannot change that.
Now it's visible.
Okay. Right. See, increasing, and see, max. It goes maximum up to around 12 o'clock, and then again it decays. Again, you can extract this data again, export data. 1 day data will be there. So you can use that data anywhere in Excel file, in MATLAB file, in any file you can use that data. And just zoom it out and see everything, scale data, baseline data, anything you can see here. This is complete here. Month wise you can see, and here you can see from different issues, say hourly, monthly. See, you can change, you can see DMAP. You can see profile every month's profile, different profiles. You can see PDF function also, histogram kind of thing, CDF also, DC also, everything. These are basically kind of maps, nothing else. Right.
Excuse me, sir.
Yeah.
Sir, sorry to interrupt you. Could you please explain what are D maps?
Sir, DMAPs again, it gives you the, say, complete data on the same scale. Like when we have a hybrid system, right? Right now, what happen is, like I have only solar radiation data, right? Only one component is there. When we have all mixing data on the same platform, so you can extract that data again same by clicking on the same data. So you will got. I will show you later on, right? When we will simulate this part, right? I will show it on. We can extract all data. This is data extraction and nothing else, right? So where are we? Yeah, okay. What is this? Yes. Okay, right. So we can see that all this data is available. These are basically kind of plotting, nothing else. So you can, point is, you can take data and you can plot whatever the kind of, say, let's say you want to use a histogram, let's say, for an example. Histogram, you understand, right? This is a curve, it is a bar chart, right? And you want to plot it in a, say, line or in a dots, in a something like that. So here is no plotting system. It is a fixed kind of map, right? So let's say you want to plot it in a histogram. How many times in a year, let's say, solar radiation was 10, yeah, 1 or whatever it may be, jo bhi value or whatever the value is. Then How you are going to do that part is, if you have data available with you, you can plot it at it anywhere. That is the best part of this. So you can extract that part, right? So these are all say, and you can find it, you can help it, you can get a help. What is this all say data is all about, right? Right. So these are the basically how we plot the data. Nothing else. This is up to you how you see. You want to see into DMAP, PDF, or whatever the annual scale, whatever the say method you want to see, or you want to see data only. Let's say, for an example, you don't want to see any plot. Then you have data, and after you have data, you can plot. You can go to any mathematical presentation of data. That's basically mathematical part, right? Constraint you can give minimum annual shortage, zero. We can minimum renewable fraction. Let's say we have a system where I am putting diesel also, right? And I want that at least 50% of power should be from renewable sources, at least, or I want 100% power should be from renewable. So I can give that fraction. Operating reserve and all this, all power system component. Solar power output, I want 50% at least. Wind power output. These are the all constraints. Again, constraints are there, 50, 20, whatever the constraints you are giving, it is going to be take it. Saving is there, anything. So now you see, so far we have taken the data. Let's see. I'm going to put some wind turbine also in this, right? Right. Clear? Now there is a wind turbine in this, right? So I'm going to again connect. Again, there are some say inbuilt turbines are there. See here, you can see here, right? Let's say I'm taking generic 1 kilowatt turbine. Now the characteristic of turbine, say again 1 kilowatt DC. This is a DC turbine, right? Suppose you want to have your own turbine, so you can go for the new. You just give this characteristic curve, wind power output curve, characteristic turbine curve. That turbine curve vary from turbine to turbine. You just feed that curve, and characteristic will be generated. Power will be generated according to the formula only. If power is less, again the mathematical concept will be remain same. Like if how to find out power from a wind turbine, that is formula is there. If power is less than minimum cut-in speed, this is the say wind power. If power lies between cut-in speed to rated speed, this is that goes according to the velocity cube. If power is between rated to say cutout speed, rated power will be generated. If wind speed is greater than cutout speed, no power will be generated, right? So that formula is there. That's how we calculate the. Even mathematically, we can verify the things, right? Suppose how much 1 kilowatt solar photovoltaic panel will generate in a day. If you know the solar radiation, I know the formula, and derating factor I have given 80%. Let's say so GT into 80 into 1 into जो भी solar radiation divide by 1000 watt per meter square, right? So you can even match your power with the you can cross check your power, right? So if you have, like, see, you can give a power curve to this, that 3 pay there is power generated 1, so you can design that part, right? See, this is particular one turbine, this generate in such a way that if this is the power, this is the wind speed, it will generate in this speed, right? So if I'm not using say any new, I'm using inbuilt power, so I'll just select it from here, and AC or DC depends upon me. So again, let's say I'm taking this generic G 1.5, this is 1500 kilowatt AC turbine. So when I clicked on this, say automatically it should go to another side of the system. See, when I click OK, it should be on the AC bus. See, right? Because now I have selected a AC turbine. No converter and say nothing is required in that case, right? So there will be a separate window for that, just like in Zoom and shit.
Nothing.
No, it is just one.
It will be here only, right? Suppose you want to use your system in somewhere, then you can print it. Print means you can go to the print screen and it will be in. You can use that technique only. Suppose you want to cut this system, you want to use this system in your paper or somewhere. Yes.
Yes.
This is screen.
Suppose this one.
You want to means use this screen, use this system. You just yes you just go to print.
Actually, I was talking about
No, nothing. There is nothing like no, nothing like that. Right?
No systems, no larger systems we are going to integrate.
No, we can go up to some. See, if I am going to increase the number of say generator, all these value. See, yes. See here. See, the size will increase automatically. It will increase, but you cannot take it out from the system, right? Like you want to use, so you have to cut that. You have to do that part. There is nothing like you cannot see the system separately, right? So, oh sorry, I was using wind turbine one, right? I'm not using any generator right, so far, right? And I'm not using even battery too. So this was the system. So I have selected one turbine. Let's say I have selected 1 kilowatt DC, or I have selected any another turbine. It is also say new. I have this is 30 kilowatt AC. I have taken C. Few inbuilt turbine are there, right? And see. So again, I can have a new turbine. I can give the characteristic and I can have a new turbine. Now the point is, I'm looking for the cost. Let's say this cost me 3,000 per kilowatt. Every cost will be in kilowatt only, right? Suppose let's say operating and maintenance cost is 2 kilowatt. Now you see, suppose I have a cost variation. Something is up to 30 kilowatt, let's say up to 1 kilowatt, the cost is 3,000. If I go for a bigger, up to let's say 5 kilowatt, cost is 3,000. See, and above, if I purchase a turbine from more than 5, the cost let's say reduce 6. I can give here automatically. Let's say 6 kilowatt turbine just cost me 16,000. See, right? And replacement cost again 16,000, and operating maintenance whatever I am giving to you. See, hub height again I can change. Suppose I have a turbine hub height of 25. Again I can put sub-sensitive values. Suppose I have a same turbine, same characteristic, but I change the hub height. So basically what will happen in case of wind turbine, the power is only dependent upon velocity, area, and see velocity of the wind velocity that increase with the respect to height, right? More is the height, more is the wind. If the scale data is let's say 7 meter per second, and that is so what we do is we fix a hub height here, right? 25, and we take that data. We have to match that data also. Suppose you have taken that data, wind speed data at a 50 meter height, and you are taking hub height of let's say 25 meter. So you have to adjust that. So what we do is we keep it simple. It according, and you can find out how they change. See here. See here. All this thing. See here. The wind turbine hub out is height from ground with the rotor seat. Hub height typically range 25 meter. 25 is like that. See, and you want to say change this. These are the total capacity and see. Yes, excuse me, जहाँ पे connect किया था. Hello. Hello. Somebody asked me what is DMAP. So you can go to the help file and you can find all the details of DMAP. See.
Yes, sir. Thank
Yes.
you.
Yeah, you can find out see what exactly DMAP is, right? So a DMAP.
Here is a type of remote query was aware of hourly data.
Yes, you just whatever the query. Hello. See, whatever the
Yes, sir.
query you have, you just type here. You will find the answer. How wind
Sure,
turbine?
sure, sir.
Right. See, DMAP is there, right?
Okay, okay, sir. Thank you.
Now, see what I was talking about wind velocity change with height. So how that change? See how we got a distribution site. See these all formulas are there. This is Weibull distribution is there. See Rayleigh graph is there. Wind histogram is there. How we calculate see function the wind velocity that is a function of two parameters say wind speed. Weibull shape parameter, Weibull scale parameter, Rayleigh function, Weibull function. Every plot on a site we find out. Why we do this? All these things is suppose let's say if I have a site and then doesn't fall in this graph. Let's say right. I have a particular wind site and that does not look like the graph of the wind speed with respect to probability. Doesn't look like a Weibull function. It goes up to let's say ramp signal. Let's say this graph at a particular site. So I'm not going to apply that. I'm not going to apply wind system at that particular site. So that should be the shape of the curve should be Weibull function. And most of the time we don't even care about Weibull function. When we take k equals to 2, we talk about Rayleigh functions. So Rayleigh function is one of the best site for the wind turbine wind location. If the graph wind speed meter graph is like in the k, you can see the green one, the third one from above. This is the best location for say to install a wind turbine. So that's why we do all this data analysis, right? So again, here we have given so many variable, okay? Lifetime, hub height, everything. How many quantity I have to consider? It's up to me. Let's say I want to keep it up to 6. I don't want to use more than 6 turbine in this system. So I can put a cap. That's up to me. Suppose I don't want I want maximum. Let's say I want a hybrid system where I will have only one turbine. So limitation is there. See, so here I can give the limitations. Now it will simulate only for one turbine. Suppose you keep your option open 1, 2, 3, 4, 5, 6, 7. Now it will select from 7. So maximum every time you have to give the maximum and minimum value. Suppose you don't want to go up to 7, you want to only use only one turbine. So simple. So at my final answer it will be one turbine, right? And again new you can find out, you can do so many things. Again you can go to the help and you can find out whatever the say what is the baseline data, what is anemometer height, see what is autocorrelation factor, what is say attitude, what is say how the things change, how it calculates, see everything you can find out. Very even the interesting part is it looks very simple as compared to the books. If you find out any solar photovoltaic or wind turbine book, things will be more complicated. You will see hundreds of equation are there. At the end, which equation, azimuthal angle, and they complicate things. So, like you cannot find out what will be my power. But if you go with the hammer, you can find out very easily. There is only 3 equations or 4 equations. Say you can find out, right? Right. So everything is there. See here. Say this is the histogram. See. So everything is there. See. K value. Everything is there. See. Every part of wind turbine, every part of say Everything is there in this, right? So far what we did is we have connected the system, right? Now if we have every data available with us, we have feed all the data. Now data will take real-time data. Real-time data means in my country, what is the value of 1 kilowatt PV cell? I will take a realistic data first thing, right? That in my country, let's say one PV costs 60,000 rupees. So I will convert that 60,000 into dollars, and I will take the real-time data, right? Once you have collected all data, see, I have not taken the temperature data, so it will show you some warnings here. I have not given any temperature. Suppose I give minimum temperature 12, say in Fab it increase 15, 16, 17, something like that, 18, 20, 25. If I'm not taking temperature into consideration, I will go to PV and I will remove it. That's it, so simple. Because in that equation, I am looking for only solar radiation. I don't care about what is temperature is. The temperature is removed from my equation. Now I'm going to calculate it. So I have just taken the random variable, so you can take actual data and you can go. Now I will calculate this value. So it will start working like this. Now you see what happen is if it gives you some warning, right? So we have to read these warnings first. It says Homer found no feasible solution because the maximum annual capacity shortage constraint. We have just click any value somewhere, right? To fix the problem, it will tell you what to do. Try one or more of the following suggestions. Consider a large PV, right? Consider a large number of wind turbine. Add a generator. Consider a large battery bank. Increase the maximum annual capacity shortage on constraint window. So it will tell you where you are now. So let's say constraint value will see whatever he's saying, this software is saying, you go to that. Let's say PV, we can increase PV. Let's say 100, 200, 300. Again, we run for it. Again, if you don't find any solution, we just give it some feasible values. Again, there is some problem, right? So in such a way, we can give maximum number. We don't have any problem, right? We don't have any problem. We just give a feasible data and see why this thing is happening, because we have a 54 kilowatt peak load. So we have to adjust the thing. So I'm going to increase all this size and then things will become. So I'm just taking a whatever I have designed one system, I am taking the just because this value I defined them.
Excuse me, sir.
Yeah.
So the PV and the battery bank connected to the DC bus.
Yeah.
Since we haven't connected any converter between the DC
Yes.
bus, so I believe they are floating. That's why we are getting the error.
Yes, absolutely right. So I converter, add converter. But before we ever did the converter, I have not seen the part. Right? Sorry. Let's see. Yes, we got the data. So it's going to see more is the sensitive analysis, more is the variable I am increasing, more is the time it took. Now you see, can you see it running? Can you see it simulation running? You can see that.
Yes, sir, we can.
Yes. Now you see the sensitive analysis. You see sensitivities. I have given so many randomly sensitivity to this system. That's why it will run up to 126 time, and each simulation will run up to 4104 times. See, so it's going to take more than 1 hour. See, 11, 12, 126. You can see every time it reach up to 4104, and it again repeat for the 13, 14 like that. So I have just given it some randomly sensitivity, so it will show you the results, right? So it will run like 126 times. So I'm going to stop it, right? Now see. So this will run like according to this. Now these are called optimization results. Now suppose I'm just taking it. Uh, I want to select this, and this will be according to the say CUV. I just randomly stop this value. So I'm just taking one. Already I have built a file, and I'm just going to open that file. Right. I'm going to take wind plus PV plus battery. Okay, I've just taken one file, right? Result is already calculated. So in this system now you see, I have taken two load. One is domestic load, right? I have given the values. All I have taken another load, that is community load. To load I can give even add some deferrable load. Deferrable means whenever there is excess electricity, it can be served or something like that. I can give some heat load, thermal, hydro load. I can give that part, right? I have given this cost analysis, one panel size consider up to 1000. It's up to me. Genetic, I have given some values. So batteries again, I have taken maximum values. Maximum. You can go up to maximum. There is no problem as such. So now you see, I will analyze the results. See. So when we calculate it, so it gives us result in such a way, like these are called optimization results. Now we can see overall also this how much it has taken. See, this is the overall result of obtained from this software. Now how to analyze, how to justify the things, that is the point. Now how to select the system. This Homer, what this do is this select system, and this for this particular load, it has selected a system that is a hybrid system that has 100 kilowatt panel, right? 40 wind turbines, right? No diesel, we have not added any diesel, and 1000 batteries, right? 45 kilowatt ka converter, and the capital initial capital cost is 592 lakh, 5 lakh 95,000 total. Operating cost is this, total NPC is this. Cost of electricity is something $0.518 per kWh, and rest is they see in all increasing systems. See, 0.4. Next combination is this. Here it has selected 100 kilowatt, 140 turbines, 1000 battery, 100 kilowatt converter. The cost increase. So in that way, even that you can find. See, if this system is totally met by wind turbine, here you can see in this result. See, there is no PV involved in this system, right? You can see there only wind turbine, battery, and converter is there. See, no PV is involved in this system, but the cost is 0.775, and there will be some cases where PV and battery will be there. So it's up to how we design the system. Now, how to analyze these things. Now, again, once we got a optimization result, we'll see what we got, how much electricity it has generated, what happened to the battery, what happened to the turbine, right? So we just double click it. And if we have given some sensitivity analysis, it will show up in some window. Here you can plot according to the sensitivity. Let's say I have given a sensitivity of if fuel price increase, what will happen to the cost of the system. So I will, when I will use a diesel generator, I will give a fuel price change. Let's say if I have that file available with me with diesel. Can you find out? Yes. See, right? So in diesel generator, let's say.
We are seeing only one yellow line.
Yes, I will plot the generator. I will plot the data. I will plot. See here. I will give the sensitivity first here. Let's say when I put a diesel generator. See, first I will see what is the fuel. Next part is fuel. I'm using diesel. Let's say, right? So diesel I will give you coefficient. This is one equation is there when diesel generator to calculate the power. The load is adjusting, sorry, the power is adjusting, power is calculating according to the, say, fuel input also. So A square, B square, some equation is there. So according to that we calculate. And we are not supposed to, say, run on full capacity. Suppose sometime I have a generator of 1 kilowatt and I need 0.5 kilowatt power. So I'm not going to run it 1 kilowatt. I'm going to run it for 0.5 kilowatt. So what will happen in that case? The fuel input will be different, and that is non-linear curve, right? It's not like that ki half rated hai to half liter it will consume, something like that. It has some particular equations, right? So if I don't have a larger load, I will run diesel generator according to my system. In that case, every hour, suppose, see, fuel input change, right? Fuel input change, money change, because you are buying that fuel. See, and see, these are all calculator output, fuel consumption. You can have generator size, whatever, and see, there will be some another. Now you see, here in this Homer, you can find out so many fuel input. Let's say biomass, biogas. Now it's a biomass generator. It becomes automatically biomass generator. The type of input depends. Say input generator. See, diesel. Instead of diesel, you are using ethanol, methanol, natural gas, whatever the system fuel input you are using. Now you want to, say, schedule it. Again, there is a facility in this software. Suppose you want to schedule it on, you want to keep it optimized. When it is required, it will run. Suppose you want to force on, let's say. So I want all January it should be, let's say, on, forced on. See, and I want to it forced off. Let's say I don't want to use generator in, say, January. I have a constraint. I don't want to use generator in December. I don't want to use genuine generator in these 2 months also. I don't want to use, say, generator on weekdays in April. See, and I want to use it only for 2 hours, let's say, in March. That's it. So now, and I want to use it at a full capacity, let's say. What will happen in that case if you are going to use it for full capacity? It will run for full capacity, right? So there will be some windows there. You want to use, right? You go to this diesel resource. See, you can change here price. Let's say $0.8 per liter, and you want to see the effect of changing of price. Let's say tomorrow there is $1 per liter. Next day $1.5 per liter. Now, when you will see the optimization result, right? Here you can find out generator some ratio. Yeah, minimum load ratio is 30%. You want to keep it 100%. Say, it means it will run on full capacity, whatever the load is. Let's say you have a 50 kilowatt generator, right? And load requirement is 10 kilowatt. So what will happen if you don't consider it minimum load ratio, 30% or whatever the value is? So what will happen now? See, what happened in case of generator? The complexity of the system increase, because see, life time of generator is operating hours, not years, right? See, generator lifetime is operating hours, 15,000 operating hours. So you are going to make it force on 15,000 hours. So you want to make it on full year. That's a generator. So within 2 years you need a replacement, because in a year 876 is number of hours. In 2 years it is exceeding from 15,000 hours. So one constraint is that you want to keep it minimum, so that the life of generator become more. See? So in that case, you go to that window, and here we can analyze everything. Is the cost of electricity is $0.518 per kWh, and here I can see how much electricity generated. What is see here? This is net present cost. PV this much. So I will take some feasible. Okay, let it be. Replacement cost is there. If I click on the analyzed, say, cost type, analyzed cost type, generally Homer use analyzed, and we want analyzed cost system. Analyzed means what is the expenses for 1 year when we have calculated everything from capital to and that we have calculated everything, salvage value, replacement value. What is the annual expenses, maintenance cost, everything we have included. So the manual analyze is this much system, 7636 dollar per year. How much load we have served, that will give you the COE, cost of electricity. So Homer calculate analyzed cost. Analyzed means for 1 year how much we have spent, including everything, including capital, including purchasing of devices, including replacement. You see, here again you can call this data export data. Here you can save this figure. This is again, and you can analyze even more deep by component. See, by cost type. See, capital, replacement, operation. See, you can see the details. See, everything you can see. You can compare in even see this system to this system. You can compare. If you have only wind and you can have this, what are the things which is different except the cost? See, everything you can compare here. Cash flow. Now you see, cash flow is generally people from finance understand that cash flow, we how much we are giving and how much per year we are taking, something like that. If we put it on negative side, expenses, and earning we put on upper side on the horizon. See, this is the capital, 6 lakhs is the capital, and these small are say operating and say operating cost, and you see the replacement cost. It happened after 10 years. The battery life in this system, if we have managed SOC and everything, the battery goes up to 10 years. The next battery is replaced by or something, another component. By component you can see by cost type, by component, by display, anything you can see here. Discounted rate, everything, every cost, say you can see here. Now see the electrical part. Now see, this is electrical part. See, in this system, the primary load is 173680 kilowatt per hour, right? Total load is 173680 kWh per year. PV array has generated 367257 kilowatt hour per year. Wind turbine has generated 622 kilowatt per hour. Generator has generated 821 kilowatt per hour. Total energy we have generated by this system is 368700, 100%. Now you see, we have generated 368700 kilowatt hour per year electricity from this system, but the problem is that we have served only 173680. So this is the excess electricity which is goes wastage. Suppose you put a deferrable load, you can use that electricity, and we are paying only for 173680. So the cost of electricity will be annualized cost divided by, say, sorry, number of units divided by whatever the money is required. Now again you can take this data, export data. Again you can find out how much, even see hourly you can plot this data. See, when you go to this window, you can see what happened on a particular day. I will take example of, let's say, first day. What happened to the 1st January? Say, right? So I'm going to make it. First, I'm going to see primary load. This was the load in that system. I have designed this system. So this is the load. Right? Clear? I have taken load. This is different system from the very first system we have started. This is PV power generated. See, can you see this one?
Yes.
PV power generated. This was the load, and this we have generated 2 kilometers, something like. This is turbine generated power, blue one. This is generator 1 power. Generator has not generated anything because it doesn't require. We have enough plenty of. Now you see, load is very small, and PV we have generated a lot.
We are getting only load value.
Yellow is there.
Yellow as well.
Yellow.
Okay, yellow one is
Yes.
Just like this.
Now see. Can you see now? This is the power.
yellow is visible now.
No, but I cannot change the color. See, this is primary load, right? I can make it in 2 window. Now you can see
Okay.
yellow one. This is PV power generated. Now you see this is wind power generated. This is generator power generated. No power is generated by generator.
It's not visible. Okay.
Again, yes. But I cannot change the color. Sorry.
Exactly.
And this is the primary load, sir. We have completed, and this is excess electricity. See. We don't require this electricity right now, but upper portion we don't require. This is excess. If we have a deferable load, we can give it to the deferable load. But this is not counted in money because we are paying only for the what we got, what we received, right? So this is excess. We can go to deferable. Now see, unmet load, nothing. We have all load met, right? Inverter power input, inverter output, rectifier input, rectifier output, battery input. Now you see battery state of charge. See. First we have taken from battery initially when there was no solar photovoltaic, right? We have taken from battery, the black one, right? When power comes up, we are feeding to the battery. See, in next January 3, again it goes down. See. So battery, we are taking from the battery. How much power we are giving to battery? How much we are taking from battery? We can see. See. I just want to consider on battery only. See here. See, match the graphs. In first hour, January, we are taking some power from battery. Below 0, we are taking power from battery. 40 kilowatt power. See, this curve is going down. Again, we are taking power, and again in second hour, see, we are giving power to the battery. See, again we are taking out from battery, and complete year we can see what happened to the battery. See this one lower, and you see every time the SOC of battery is maintained. See, the state of charge of battery never goes beyond 30 because we have fixed the mark 30. Right? See, 20, 40, 60 and 80, 100. It never goes down below 30. So what happened to that 30? Now you see, you just imagine that. What happened? This is approaching towards 30. That means this is a critical situation where battery has low power. So at this time there should be some wind or generator kind of thing. See, so I'm just going to this date, July, where SOC is very less. See here. Right. So let's see what happened on that day. So see here. See, generator is all the time silent. See. Right. all the time generator is not working because enough PV and everything is there. See, no need of generator in January, February, March, April, May, June, July, whatever. All of a sudden we required a say generator, and this work only for very few times, very few say system. See here because state of battery is not okay. Yes, negative is and power required is say load is always there. See, this is a load. So here we required a generator. And if we don't have this generator, we have to increase the size of battery bank so that it doesn't go below 30%. So system will be changed. Suppose I remove diesel generator from this, everything will be changed. And again, you can analyze this data and you can enjoy with this data. See, whatever again the same concept is there. Whatever maps you are going to put, you are going to use this data in your MATLAB programming or somewhere, whatever. See, and this look again. See, anything you can export again this data. See results. I am going to export this. See, again you will have a Word file where you have all the data with you. See, where I have stored. Export data. Sorry. Now you see. Now you see. You have complete data for 1 year. See, you can analyze from here. 1 hour primary load is something 35. You can see primary load PV power 0. No power is available. At 6 o'clock there is a little power available. This is inverter output. Power from battery. You can see from say above what are these parameters. Battery state of charge. Now you see the battery state of charge. You can see from here the battery state of charge is 90% right now, and we are taking from battery 39. This much of power we are taking from battery. So battery state of charge will go down, right? See, and minus 44 is required, and we have enough, so we can do that part. We can go, and there will be some time. See when it goes 30 somewhere in July. See here. 30.33 is the state of charge, and you required minus 29 kilowatt power from itna value. So battery cannot give you because you have put a constraint of 30 kilowatt. Some another. Now you see generator will be there somewhere. See the 6.49 is from generator, right? So I will take one grid connected example also. Let's see what it says. I will take. Yes, I've taken it. I've designed this biomass with grid hybrid PV system, right? So again, when you connect to the system to the grid, you are supposed to feed the electricity price and all that part. See here, I can feed price sell dollar per kWh 0.1 sell back demand whatever, and normally it's like that in some state like when you give power to grid they charge a different rate and you take power they charge different rate, and if you are providing to the grid almost in some state they will
Larger.
yes
They provide
very large amount. No. When you give to them, they charge you at a high rate, and when you take, you are normal customer. Yes, like if unit is 5.5 rupees, that is for everyone. If you are selling to the grid, they will take you from like something 7 or 8 rupees like that, right? So again, you can have sensitivity here. You can take even real-time prices. You can import price data per hour. Yes, stock market. You can do that part also. Every time what is particular hour, what is data, you can do that part. Emissions you can see, you can control, and you can see if you are using generator, how much CO2 is emitted to the atmosphere. You have used the generator, so how much you have emitted sulfur dioxide. Everything you can see from this software, right? Advanced C, interconnection charges, standby charges, sale capacity. Now you see that we have a limit on selling. Because why we have need limit of selling? Because every time what we are generating is something like if we have AC DC system, we have a problem. Because you suppose you are generating power from PV, right? So you need to sell to the grid, and grid is AC, right? So every time you need to put a converter. So convert, if you are putting a cap on converter, so that means converter is going to convert that much of amount. So there will be one issue. So this, let's say I can sell capacity. I can sell 100 kilowatt only. Maximum value is 100 kilowatt. In that means I should have a converter more than 100 kilowatt. I have to feed the load also, plus I have to sell grid also. Purchase capacity. We can go in a dual way. I can purchase up to 10. I want to keep. I want to design a system where I want to purchase minimum power from the grid, and I want to feed maximum power to the grid, and still I want to have benefits. So I have designed this system, see, in such a way, and you see the results, overall results, and the cost of electricity, that is something like $0.417 per kWh, still costly.
Yeah, there are so many optimized values.
Yes, optimization, and they are sorted out according to the COE. See, sometime what happen is few parameters is changed. Let's say some other values are there in this 190 PV he is taking, and 42 something will be there, like renewable fraction is there, biomass ton is, everything will
Cost per watt, that is what we are required to see.
yes.
Our constraint is
Our constraint is
our objective is
minimum, right? Obviously. So this is according to, let's say if you are not using PV, so it will show you the result that only you biomass and PV, and if you are not connected to the grid, you can have this COE. The feasibility we have to check. It is feasible or not feasible. Let's say this system is something 0.417 rupees it gives me, right? 0.47 rupees is too much number. Let's say 60 rupees dollar is there. Still 24 is the cost that is coming to me. So I have to check this system will be feasible or not. And I have, let's say if I apply some subsidy and I reduce the cost of every component by half, let's say. Suppose I have designed this system and government give me subsidy, okay, just reduce the price, every component price half rate, right? Now the cost will be obviously 0.2 something, $10, and $10 rupees is a very good number as compared to I'm generating my own system. And again I can check how much electricity I am feeding to the grid. See, I am just purchasing, see, this system is very good. I am just purchasing 13678 from grid, and see how much I am selling to the grid. 275,146 kWh per year I am selling to the grid. So this is a very good system. In fact, cost of electricity is, so what this 27516 kilowatt per hour they are receiving from nowhere. Cost is not a factor. They are receiving this much of power from all kind of renewable energy sources. No pollution is there, nothing like system is there. If you are going to generate this much of power from diesel, now you can compare it. If you are going to, yes, how many pollutant emissions will be there, right? So again you can find out all how much time this generator runs, how many times it we have to start this generator, right? What is operation life, what is capacity factor, what is cost, what is electricity production, what is output, everything, every data you can find out. And you want to have a plot, you can, again, the export data is every time there. See, converter, in input, output, everything, and you can say grid. See, net. See, in month of July, I have purchased 1914 kilowatt energy from grid. I have sold 20,000 kilowatt energy to the grid. Net purchase minus हो गया. Peak demand, energy charges 0. Energy charge -2. That means I am earning from, say, grid, right? So this will be somewhere when I see the calculations. So this will be showing my income. See, negative side. The only thing in this system is negative when system is connected to the grid. Otherwise, everything is positive. Yes, we have expenses only. The only income which I have generated is see from grid only by selling the electricity, right? So there are so many, and the best part is just I want to come to the my PPT slide. Then this software has a very say wide range of applications. I have just shown you the 3 or 4 data. Like I have taken wind, solar, and say biomass. And you can go for small hydro, you can go for fuel cell, you can go for diesel, you can go for flywheel, battery storage. So many variabilities there. And in last, I am telling you, in 10 years, almost more than hundreds publication I have seen where people are using. I will show you one publication. See, few publication I just want to share with you where people are using these software only, and they are getting very good publications. See. And but the only way is how they are presenting the material. See how so. Sorry. You can find out all these paper are from Homer only. I just want to share any single paper. Can you see any application of Homer kind of thing? Now you see. Can you see? Yes. Say this is latest 2014 publication, almost 1 year back. Off-grid electricity generation with renewable energy technology in India and application of Homer. Just simply one application. And best part is there is no cross check of your results. These are not standard results. Simulated result. No cross check is there. So you are the only owner of C. Now you see this figure looks similar to you. And this is not a very good reputed journal in energy. See, he has taken hydro, PV, wind turbine, battery converter, and biodiesel generator. See here. See all. Even he has not done the. He has taken the same graphs by clicking just simply bitmap. See all this data is he has taken. See all this. This is nothing. No, just right click and take this picture only and nothing else. Once you feed the data, and you have to just write the things. See, all this data is available. Any another paper you can see. Anywhere see every time you can, and you can analyze so many applications. See, once you have a data with you, you can go for solar, you can go for wind, you can compare them, you can add one part in them, and see you can see now these graphs look familiar to you. See, every time these people are doing the same job. See, and they are very all paper in very good reputed journals elsewhere or something like say. See all data is there. Homework is there. See all. They are just comparing that if you put a grid in this system. If you put this system, these all these graphs now looks familiar to you. See, there are so many. Even I am saying there are hundreds publication on this Homer. And nowadays people are doing. They are say what I do is suppose I have a system, right? So in this, I don't know how Homer has optimized the systems, right? So what I do in my research is I mathematically prove that part. Suppose I generated power from PV according to that formula, and yeah, mathematical modeling, right? And there you can apply some say kind of techniques, and you will always find that this Homer is nowhere with respect to techniques, because in techniques you know what you are doing. In Homer we don't know what we are doing. Once you have feed the data, you are free. You just click simulate, and that will give you a result. So you can find out. See, if you are interested, you can see one of the paper I recently published. Uh, yeah, this one is there. Now this is optimal sizing of grid integrated hybrid PV biomass energy system using artificial bee colonialism. In this, what I did is I take a reference with Homer, and I applied this technique, artificial bee colonialism, and I have taken the system PV biomass. So this is a limitless opportunity. You can add like say PV biomass wind. New concept is there, so you can model that part, right? So people are doing like that. See, grid integrated photovoltaic energy system. Yeah, photovoltaic energy system, battery and grid. So opportunity permutation and commutation is see application to Homer. Though not supposed to say converted the things. I think thank you very much. And if you have any query, any doubt, please, I will try to solve. Yeah, please. Thank you. Any questions? Yeah, from your side. And you can download it very easily. Right?
Hello.
Yes, sir.
Sir, I want to. I am from MMU Milana.
Yes, sir.
I want to ask a little question that
Yes.
is it possible to have the dynamic response of the system, particularly in the term of current and the voltage?
No, sir. I mentioned this thing in starting only. We don't have power system components involved in Homer. We don't know what exactly. Yeah, so we here in this drawback with this system is, sir, that we don't know what exactly going on. Exactly going. We only talk about power and KWS. Nothing else we talk about.
Because you have shown a lot.
Yeah, we cannot see, sir, dynamic response. There is no such concept like P, Q, what is harmonics, what is current, what is voltage, nothing like, sir.
Okay, it's just the economic investigation of the system.
Yeah, that is totally different domain. If you want to go in that part, you have to go for the Simulink system. You need to Simulink a model of wind turbine, then you can see what is P, what is Q, what is current, what is voltage, everything. There you can see. But here, this is more economic aspect software. We talk about money here, not power system qualities here. We don't even know that the system we design is okay or not, because we design on the basis of previous data. What will happen is, suppose next 4 months, like one complete month, there is no resources available, no solar, no wind, nothing. So my system is totally failure.
And one thing what I have observed in the various results, that in India we are more concerned with the rupee, not with the dollar sign.
But it doesn't have a option for dollar. So what most of the research do, they calculate the money from money in form of dollar, and then they multiply it with rupees, and they write result in rupees. I can show you one paper if you want. See.
Sure.
See here. This is from Swarm and Evolutionary Computational. They have applied a BVO algorithm from India side only. and they are talking about Homer and everything, but they have considered rupees in, say, money in rupees. PV capital goes 2000 rupees per kilowatt, and all these calculations they have done in rupees. So they have converted, they have feed data to Homer in dollars, and again they, by using the current rate, they will mention somewhere that $1 equals to
So
something.
manually we have to calculate the equivalent value in the rupee, na?
Yeah, definitely, definitely. There is no provision for rupees, euro, something like that, because this is designed by USA. So only things it understand is dollar, nothing else. Thank you.
Okay, thank you.
Excuse me, sir.
Yeah.
I'm Ranjay Singh from DIT University,
Yes, sir.
and I like to personally thank you for your intellectual lecture and introducing us to this new software that is Homer. Because earlier we had heard of it, but we never knew the potential of this software. So, heartiest thanks to you for introducing the software to us. And if we could have your email ID so that we could get in touch if we have some issues relating to this software, that would be very nice of you.
You are calling from
DIT University, sir.
DIT Dehradun.
Yes, sir.
Yeah, you can find me from our website, Electrical Engineering Department.
Okay.
Right?
Right, sir. Right, sir. Thank you.
You can find my email ID, mobile number, everything you will get from there. Right?
Right, sir. Oh, right, sir. Thank you.
And in case you want, you can write it. That is Shakti.Singh. You can see the first slide, Shakti.Singh@thapa.edu.
Thank you, sir. Thank you so much.
You can note down it. Right. Thank you. Thank you very much. Right time.
I was watching, so I saw like you were showing your last papers, so I understood it is going to get over. So I came. You're showing your publication, so तभी मुझे लगा कि it is almost end.
Thank you very much.
So we have come to the end of the session, and I thank sir for coming such a long distance and introducing us. And this, I also came to know today that it is an open source software. That is a very big advantage of this because it is available free. Anyone can download and use it. And thank you, sir, for coming such a long distance and giving us, like sharing your knowledge with us. And with this, we come to the end of the session, and tomorrow is the last day. We have 2 more lectures left. So we have one Dr. Tilak Thakur from Punjab Engineering College, University and Technology, and another lecture from Abhishek. He is from EMC Squares, US. So we have 2 more lectures left. So tomorrow, and I think around 2:30 we will have the valediction tomorrow. Okay, so tomorrow we will have the valediction at 2:30. Okay, so with this, like this, we have ended the session, and I request the participants here to have the tea. आपसे मैंने तो भेजने के लिए सोचा, फिर आपसे तो सिग्नेचर हो गई थी.
कहाँ पे?
यहाँ और यहाँ. आप
हाँ।
कि वरना आज लास्ट डेट हो गया.
अभी वहाँ पे चले जाओ.
और कहाँ पे मैडम?
मलकीत मैडम के पास चले जाओ.
मैडम और कहाँ पे?
Yes.